radiation measurement. Good morning, sir, Dr. Masashi Kato, sir. It is a great honor to introduce our distinguished speaker, Dr. Masashi Kato, and an accomplished and a researcher for Nagoya Institute of Technology, Japan. Dr. Masashi Kato obtained his bachelor, master, and doctoral degree in engineering from Nagoya Institute of Technology. Completing his PhD in 2003, his strong academic foundation led to groundwork for a significant contribution of semiconductor science and electronic engineering. Following his doctoral studies, Dr. Kato began his professional journey as a research associate at Nagoya Institute of Technology, where he served as from 2003 to 2008. He was subsequently appointed as an associate professor in the Department of Electrical and Electronic Engineering, a position he held for several years while actively contributing to both teaching and research. His academic journey also included international exposure, having served as a researcher at Institute of Applied Research, Vilnius University, Lithuania, further strengthening his global research perspective. In recognition of his expertise and contribution, he was promoted to the position of professor in 2023. Dr. Masashi Kato, researcher expert, lies in the electrical characterization of semiconductor material, electrochemical techniques for semiconductor analysis, and analog integrated circuit design and simulation. His work plays a vital role in advancing modern electronics, material science, and device engineering, bridging fundamental research with practical technological applications. Today, we are privileged to have Dr. Masashi Kato with us to share his insight and experts. His contribution to semiconductor research and engineering continue to inspire innovation and excellence in this field. Let us warmly welcome to Dr. Masashi Kato. Welcome, sir.
Thank you, Chairperson. Thank you very much for your kind introduction. So, I would like to share my slide. Can you see my slide?
Yes,
okay.
sir. It is visible.
Yes. So, I would like to, my name is Masashi from Japan, and today I would like to introduce our recent activity for the silicon carbide for power devices. So, you know, the single crystal semiconductor is due to the periodic atomic arrangement, we can have the band gap of the electron energy. So then this atomic periodic arrangement is important for the semiconductor material. So in the silicon carbide, we have the stacking sequence. So there are several silicon carbide, you know. If we consider the silicon and carbon atoms as the pair with sphere structure, they construct the hexagonal close-up structure. And we have the A arrangement and B arrangement and C arrangement. And this arrangement sequence is different for the polytypes. There are several polytypes, like 3C silicon carbide is has ABC stacking sequence, and 6A silicon carbide ABC stacking, and 4A silicon carbide has ABAC stacking sequence. And this sequence makes different band gap of the material. And among them, the 4H silicon carbide, the most popular polytype for silicon carbide. You can see this 4H silicon carbide wafer, and already 12-inch silicon carbide wafer are commercially available. And by using this 4H polytypes, it has a wide band gap, and it is good for the power devices. And already in Japan price system, we have Shinkansen super express were driven by the silicon carbide traction inverter. This is a logo of the new Shinkansen super express. And recently, already some electric vehicles are driven by the silicon carbide inverter. And the hybrid electric vehicle is also the substitute from silicon IGBT to the silicon carbide, the MOSFET inverter. So now the most common the product is 6-inch, but now the production line going to this 8-inch scale, the device fabrication, right. How soon? No, not already 8 inches installed in the several factories. Anyway, so however, silicon carbide is not perfect. So silicon, typical semiconductor silicon, by using the negative crystal growth during the characterization or protein tone, the dislocation-free crystal can be obtained. However, silicon carbide, we don't have a good crystal growth technique. We have dislocation, right? Edge dislocation or screw dislocation, and so it is in Japanese, but we have the several understanding of the dislocation. Anyway, there are several dislocations in the crystal. Also, we can see that it is a cross-section of the crystal, image of the crystal, and we have threading dislocation, TSD, and threading edge dislocation, TED. And also, we have the basal plane dislocation. It is a dislocation on the 0001 defects. So, this image, we have the inclined the basal plane. This is for the step crystal growth for the epitaxial layer. Without this the inclination, we have the point instability. So even on the point silicon carbide or epitaxial layer becomes the different point types the occur. So we have the inclination and the crystal phase. OH stacking sequence the exposure to the surface, and we can grow the epitaxial layer in the OH silicon carbide. And then this epitaxial growth, we have the dislocation conversion, TSD to the transfer, BPD to TED conversion. So anyway, so among them, the basal plane dislocation is most important, most harmful. The dislocation in the silicon carbide. So this is because, as I said, the silicon carbide has several point types, and this means that on the basal plane, the crystal disorder easily. This is from the particle point stacking sequence. If we have the glide on the basal plane, we have the stacking port like this. This is single chocolate type stacking port. And double chocolate type stacking port is also common. And there are several stacking ports. Anyway, this single chocolate type stacking port is easily occur because the basal plane dislocation always have the stacking port structure. Because basal plane dislocation has two partial dislocations. And between the partial dislocations, stacking ports are always located. So if we have the different lengths of the partial dislocations, the stacking port area is also different, depending on the distance between the partial dislocations. So this is a harm for the silicon carbide power device. So this is called bipolar degradation. if we conduct current in the silicon carbide PN junction, we have the expansion of the sucking port. This is a PN image for the after the electrical conduction of PN diode. We have a sucking port like this triangle or some bar-shaped structure. They are all sucking ports. And with this sucking port, presence of these sucking ports, the current or the voltage characteristics become the degrade. Before we have low or expand, we have degraded the resistance, higher resistance. So this means that the power loss during the material handling means that the dislocation cannot be mobile. So the material bending is due to dislocation factor. So this is the analogy by metal. But even for semiconductor material, we have some mechanical defect, i.e. the point defect or doping. So for example, for silicon wafer, we need to have some oxygen impurity to keep the mechanical strength. So we typically have 10 to 15 cubic centimeter oxygen impurity in silicon wafer, the standard silicon wafer. So like that, even for the silicon carbide, if we do something, we can stop the dislocation drive. So we try the approach to suppress the sucking port expansion. So then we tried the proton implantation of silicon carbide to stop the dislocation drive. So proton hydrogen ion is a widely used semiconductor process. And we tried the proton implantation of the silicon carbide crystal and device. So usually, as I explained the image, the basal plane dislocation is located on the silicon carbide substrate, and the epitaxial layer, the basal plane dislocation converted the stretching edge dislocation. But the problem is BPD, basal plane dislocation in substrate. If we inject the hole to the substrate, the basal plane dislocation easily to expand sucking. So we try to implant the proton to the substrate epitaxial layer interface. So we imagine that the hydrogen ion sticks to the partial dislocation. So then partial dislocation mobility decreases, and the suppression of the sucking port can be possible. So we tried several approaches finally we found that if we implant a proton to the bare epitaxial wafer before the device processing, so we can make the good diode electrical characteristics and with the effect of the proton implantation. This sequence we developed. Before that, we tried several approaches. After the diode fabrication, we implanted some mid-term implantation, but finally we reached to the epitaxial wafer proton implantation to the epitaxial wafer, and after that the device processing has been performed. So we fabricated silicon carbide PIL die with this cross section and the reference side the real image photograph. So we have the 4.5 millimeter by 4.5 chips with central contact area 2 millimeter by 2 millimeter with structure to see the electroluminescence from die. The right-hand figure is a cross-sectional image of the diode. We have the N plus nitrogen dot substrate with a high purity dot ratio. And we have the P-type layer with the aluminum implantation on the surface side. With that, we initially implanted proton to the substrate epitaxial layer interface. So then that we observe diode characteristics like this. We can see the rectifying properties all of the diode. And this number is a dose of the proton, 10 to the 12, 20 to the 14, and 20 to 16 per square centimeter proton dose. And without proton implantation, there are several the non-uniform electroluminescence. This dark area corresponds to the stacking port expansion. However, with proton implantation, this diode does not have the stacking port expansion. So this means that with similar diode characteristics, we can suppress the stacking port expansion after the electrical source. So without the implantation, we have the stacking port expansion like this. Can you see this video? Initially, we have the uniform electroluminescence, but the dark area expands during the device operation. So this is a stacking port expansion. So this video is for the without the proton implantation. However, if we implant the proton, we can see the uniform electroluminescence. So this means that no stacking port expansion can be observed. So here is a number. We counted the density of stacking ports, and without proton implantation, we have nearly 100 of the stacking ports in the space centimeter. But proton implantation, by using proton implantation, the number decreased to half or even 20%. So proton implantation can suppress the stacking port expansion. So this means that device reliability improved by the proton implantation. Also, we tried to the helium-ion implantation. So the sequence is similar, but the energy is higher than the proton implantation. Almost 3 times higher energy is required, but the diode is works, and we can suppress the stacking port expansion even for the helium-ion implantation. So here is the number of stacking ports area without implantation. The other proton implantation case, without implantation almost 100 sucking force density per centimeter, but even lower number after helium implantation. And also we compare similar the dose of the proton and the helium, and we can see the both species. We can see the reduction of the sucking force, but the helium case, the blue one, has a lower, even lower the sucking force density compared to the proton dose. So this means that the proton implant, helium ion implantation is the better effect compared with proton implantation. So even the other ions, fortunately, the follower of our technique has reported several approaches. For example, fluorescent ion implantation by the Toshiba group, they observed implanted fluorine implantation has also similar effects as a proton and helium. And they show that phosphorus ion is effective to suppress bipolar degradation, such expand. And also we observed the other ion effect by using device operation. So this means that point defect introduction by ion implantation is a key factor to suppress sucking force. So zero-dimensional defect can suppress two-dimensional defect. So then we can have highly reliable silicon carbide device. And also we observe point defects the distribution inside of the devices. We observe the cathode luminescence, cross-sectional cathode luminescence. And here is a spectrum of cathode luminescence. And after ion implantation, we usually have L1 line defects at the 4, 6 to 27 nanometer luminescence. And we can discuss point defect distribution by using L1 line intensity. This is L1 line intensity distribution inside the silicon carbide device. Without the proton or helium implantation, we have this graphic. However, if we implant proton or helium, we can see the L1 line, intensity L1 line, even the low deep region inside of the device. And we have 10 micron the epitaxial layer, and the deeper region is corresponds to the substrate. So the helium implantation induces the point defect near to the epitaxial layer to the substrate interface. So this point defect distribution is effective for the suppression of sucking force. And we also see the carrier lifetime distribution inside the device. This is our system, our original system, and we can see the carrier lifetime distribution. Carrier lifetime depends on the point defect distribution. And this system can observe the high spatial resolution carrier lifetime measurement. And this is a schematic of the optical the configuration. We have the high MA object length and to make the small spot on the sample surface, and we can see the 1 micron the spatial resolution of the carrier light. And we observe they are defined the guide for the carrier light the value. But in both cases, we see the carrier lifetime reduction with proton or helium implantation. So then our implantation technique can induce the point defect and reduce the carrier lifetime, and then the suppress the sucking force to expand. So anyway, the carrier lifetime measurement technique I published one review paper last year. And even we tried other approach to create a point defect in the interface, a substrate interface. We implanted proton from the back side, substrate side, and typical silicon carbide wafer has 350 micron thickness, and the high energy proton implantation induces 330 micron depth. So from the back side, even we can get point defect or near to the interface. And we try several poles, and we observe operation, and we can suppress starting pole by using backside implantation. So these results indicate that point defect in the substrate. The other reports show that point defects in the substrate diffuse to the epithelium and suppress the starting pole. Anyway, so we create a point defect in the substrate by the backside implantation. Defects from engineering important to suppress larger defect or suppression of the larger defect. So our technique, the company SHI-ATEX, the installed the commercial service named by SFE. We have wide map of this technique, and this is already installed in for the mass production of silicon carbide device. So development of our technique, this technique, we published a review paper on the last year. In this paper, we described the history of our development and difficulty to make the commercial service with highly reliable and reproducible design. Anyway, already we developed this technique to make the highly reliable silicon carbide device. Okay, so this is the conclusion, and our papers for this technique. So by using the point defect engine, using the ion implant, high energy ion implantation, we can make the bipolar degradation simple. This problem has been discussed for more than 20 years, but we found a solution of this problem. And there are the published paper. Actually, we started this project in 2018, but first publication is 2022. We need 5 years to make the first publication. But after that, we have published many papers for this technique. So if you are interested, please see these papers. And this work was supported by Nadu. This is Japanese the economic ministry branch, and my co-worker was Nadu University, Professor Harada, Nadu University, and Dr. Sakane in SHI-ATEX. So that's all for my presentation. Thank you very much.
Thank you, Professor. Thank you for your wonderful session, sir. Now the session is open for discussion. Any questions?
Thank you for the nice presentation, Professor. Yeah, I have a small doubt regarding the annealing. And is it necessary to have the necessity to do the annealing for all the ground crystals?
Annealing is for the recovery of the implantation defect. We need at least the aluminum ion implantation to make P-type polymers for the device operation. We need PF junction to create diode, even for MOSFET. So to this ion implantation induces a large number of defects. So much defect is found for the device operation. So we need to make the annealing, high temperature annealing to recover this defects. However, even after high temperature annealing, we have some lower number of point defects. Such the point defects are still effective to suppress the starting point. So we induce a high temperature annealing during the process.
And as you said, it is a very high temperature. How do you optimize the annealing temperature? How do you fix it?
Usually, so silicon carbide field, we know that 1650 to 1750 degrees C is the optimum to recover the point defect induced by ion implantation. So we use such kind of temperature for recovery of the implantation defect.
Thank you, Professor.
Any questions?
This is Babu, sir.
Yeah. Yeah, we started with the growth technique is application growth for the substrate, and the accelerator is chemical vapor deposition. So it is a typical process in silicon carbide.
The facilities with you or
Growth facilities.
Growth facility, it is a commercial product, and we don't know the details of the facility, but it is very common. Many companies grow the silicon carbide wafer accelerator. So you can see the internet. You can purchase the silicon carbide wafer. It is very common now. But typical silicon carbide wafer has many defects. So to make the electrical device, we need to choose a good silicon carbide wafer.
even the company provided crystal is having more number of defects? You are saying.
Sorry?
You are getting the crystal from the company.
Yes.
And that crystal also having more number of defects.
Sorry?
It has more defects.
But there are many defects, and it depends on the company. But by our technique, we can suppress the radiation among the company.
Yes.
So we can create a highly reliable device even for any wafer.
Thank you, Professor.
Okay, thank you, Professor. Thank you for your wonderful answering. Thank you for giving this wonderful opportunity for the convener of this conference. Thank you, sir. Thank you, sir. Yeah, thank you, Professor. Thank you for your time.
Okay, thank you very much.
Yeah, we enjoyed your talk. Thank you, Professor. Yeah.
Thank you.
See. Yes.
Can you hear me?
Your voice is audible.
Hi. Sorry. Can you see my slide?
Yeah, the slide is visible.
Okay.
Yes, wait a minute.
Mm.
wait few minutes. We will introduce you to the audience, and further we will start the session.
Thank you very much.
Good morning, Professor. Hiroki Matsu has been an associate professor at Kumamoto University since 2021. He received his PhD from the University of Tokyo in the year 2016. His research field is solid state chemistry. He has worked on the development of ferroelectric materials, solid oxide fuel cells, and photoelectrodes for water splitting. His current research interests include energy storage properties and the photovoltaic effect in various polar materials. In particular, he focuses on materials design based on defect chemistry and domain engineering. Thank you, Professor. You can start the session.
Okay. Thank you very much for your nice introduction. My name is Hiroki Matsu from Kumamoto University. Thank you very much for giving me this opportunity to introduce my research. The title of my research is this, and in this presentation I would like to focus on the defect dipole. Defect dipole is a kind of defect complex that is composed of active ion and vacant. And by utilizing this interaction between spontaneous polarization and defect dipole, we are trying to improve the energy storage properties of ferroelectric materials. This is the outline of my talk. First I would like to briefly explain my research background, and then I will explain how to control domain structures via defect dipole engineering. And then I will show the stability of defect dipole and the energy storage properties of cathode perovskites with defect dipole. And finally, I will summarize my presentation. As you know, in our electronic devices, various energy storage components such as batteries, electrochemical capacitors, dielectric capacitors are used. And multi-layer semicapacitors, MLCCs, is one of the dielectric capacitors, and MLCCs are used to stabilize electricity and reduce electrical noise in these electronic devices. And MLCCs are characterized by its fast charge and discharge rate and long lifetime. But one of the disadvantages of MLCC is its low energy density compared with batteries and electrochemical capacitors. So, however, the downsizing of electronic devices demand MLCCs with a higher energy density. So we have to improve develop the ferroelectric materials with a higher energy density. Okay. Barium nitride has been used as a material for the dielectric layer of MLCCs. Barium nitride is a ferroelectric perovskite type of site, having the tetragonal structure in phase group P4MM. Barium nitride has spontaneous polarization around 26 microcoulomb per square centimeter and high relative permittivity around 1,000 to 4,000. This is why this material has been used for the dielectric layer of MLCC. And at the temperature is moderate temperature of 120 degrees C. And this figure shows a schematic polarization electric loop of a ferroelectric capacitor. The recoverable energy density, UREC, of dielectric capacitors corresponds to the area of the green part. Though ferroelectric materials have a large maximum polarization Emax, which is attractive for energy storage applications, but but basically, if they cannot exhibit large energy density because of its large remanent polarization, ER. Okay. So, in our research to enhance the energy density, we focus on the aging effect. This is a very famous figure reported by Xiaobi Ren in Nature Materials in 2004. The red broken line indicates the PU of barium titanate single crystal. And you can see a single P hysteresis loop, which is crystallographite material. On the other hand, the blue solid line, this one, is a PU of the same single crystal after keeping at 80 degrees C for 5 days. This pinched loop is not derived from anti-flow electricity, but from characteristic domain switching behavior in the barium and titanate crystal containing small amount of impurity atoms. And this phenomenon is called aging. The researchers have believed that the aging effect arises from the formation of defect dipoles. As I have already mentioned, a defect dipole is a kind of defect complex composed of an acceptor ion and oxygen vacancy. And the dipole has a dipole moment. And so before explaining the role of defect dipoles, let me briefly introduce defect chemistry in transition metals of barium titanate. As you know, when higher valent transition metals, such as niobium 5+ or tantalum 5+, substitute for titanium 4+. Basically, free electrons are generated to retain the charge neutrality in the barium titanate crystal lattice. On the other hand, when lower valence transition metals such as iron 3+, manganese 3+, copper 3+, substitute for titanium 4+ site, the charge neutrality is retained by the formation of positively charged oxygen vacancies. So to form a defect dipole, we need to build acceptor type ions. And I have to review the trapping energy of oxygen vacancy by an acceptor ion. We performed the DFT calculations for the free energy of the barium titanate superlattice with various oxygen vacancy configurations, as shown in this figure. And this figure shows the relative energy density as a function of oxygen vacancy positions. The horizontal axis shows the location of the oxygen vacancy with respect to kappa 3+ site. For example, NO1 indicates here. This indicates that our oxygen vacancy is located at the first nearest neighbor oxygen site to kappa site. And NO2 here indicates that oxygen vacancy is located at the second nearest neighbor site to kappa 3+. As you can see this figure, the configuration with NO1, 2, and 3 gives lower energy than the other configurations with NO larger than 4. And this calculation result indicates that oxygen vacancy prefer NO1, 2, 3, and 3. In other words, oxygen vacancies tend to be trapped by copper ion to reduce free energy of the total system. Okay. In addition, it is interesting that the super configuration with NO1 is the most stable structure. Okay. And these figures are in the super cells with NO1, 2, and 3. In these figures, the direction of the spontaneous polarization are shown as red arrows like this. And the direction of the defect dipoles are indicated by yellow arrows, like yellow arrows shown here. As you can see here, the direction of defect dipoles for NO1, 2, and 3 are parallel and perpendicular and anti-parallel to the spontaneous polarization direction. As shown in the previous slide, NO1 is the in which the direction of the dipole is parallel to the spontaneous polarization is the most stable configuration. So this indicates that there is a strong correlation between the direction of the spontaneous polarization and the defective dipole. And there is a depth in the cathode of current cycling ceramics. In our research, we aim to control the domain switching behavior of cathode titanate crystal by utilizing interaction between spontaneous polarization and defect dipoles. The pinched P loops can be obtained by stabilizing the multi-domain structure with a remnant polarization of 0. In this multi-domain state, a defect dipole vector becomes parallel to spontaneous polarization direction in each domain. Due to the strong interaction between spontaneous polarization and defect dipoles. When positive electric field is applied, the polarization aligns in the upward direction like this by the main switching and resulting in the large maximum polarization. However, due to the low mobility of oxygen vacancy at room temperature, the configuration of the defect dipoles are not changed even after the application of electric field. And so, after removing the electric field, the initial domain state is restored because of the interaction between spontaneous polarization and defect dipole. In other words, the initial domain state is memorized by the defect dipole configuration. Because the recoverable energy density of this material corresponds to the area of this light blue part, a very large energy density can be expected in a couple of current titanate ceramics with engineered domain structure, engineered defect dipole configuration. Next, I will introduce how to control the domain structures via defect dipole engineering. This slide shows how to introduce defect dipoles in cathode 3D ceramic titanate ceramics. We prepared cathode ceramics by a conventional solid-state reaction. The ceramic samples are annealed at 900 degrees C for more than 12 hours under controlled partial oxygen pressure. And then defect dipole formation annealing was performed at various forming temperature TS of 150 degrees C to 400 degrees C, which is higher than trade temperature of barium titanate. In this process, oxygen oxygen vacancies oxygen vacancies migrate to the most stable position to form defect dipole. Finally, aging treatment was performed at 80 degrees C, which is lower than tree temperature by tightening. In this process, we can expect the defect dipole vector align parallel to the spontaneous polarization direction in each domain. First, to confirm the impact of accepted doping on the aging effect, we compared the P properties of under 50 ceramics and the kappa 1.5% with direct tightening ceramics before treatment. Before aging treatment, both the ceramics with PU, which is typical of ferroelectric material. On the other hand, after the aging treatment, as you can see, there is a big difference between the undoped sample and the kappa doped sample. Whereas the undoped ceramic exhibits single P hysteresis even after the aging treatment, the kappa doped with ceramic clearly exhibits a pinch hysteresis. Thus, it is confirmed that the aging phenomena is derived from a kappa in the direct tightening process. And to directly observe the domain, we performed the file response post microscopy measurement for an accepted dose direct tightening single crystal after the aging treatment. This is data for iron doped sample. We performed the domain writing test for the sample by applying DC electric field from the probe tip. These figures show the domain structures of single crystal before, during, and after domain writing test by applying DC electric field from a probe tip. We can see that the initial multi-domain structure is restored even after the domain writing test. So this data directly demonstrates that the original multi-domain structure is memorized by the arrangement of the defect dipoles. Okay, so then I will show the stability of the dipoles. These figures are key properties of kappa 1000 of direct tightening trap with formation defect dipole forming temperature here of 200 degrees C and 350 degrees. Pinch hysteresis indicating the formation of the defect dipoles are successfully observed for both sounds. In contrast, the ceramics with a TF of 400 degrees C exhibits single hysteresis, which indicates that the concentration of the defect dipole is quite low in these samples. So this result indicates that at low temperatures, oxygen vacancies are effectively trapped by kappa, forming high concentrations of defect dipole. On the other hand, at high temperatures, about 400 degrees C, oxygen vacancies dissociate from kappa probably because the high entropy state with a random oxygen vacancy distribution is prepared at such a high temperature. Based on the TF dependence of PU, the process of the formation and alignment of defect dipoles can be estimated as follows. During the defect dipole formation annealing with a TF lower than 350 degrees C, oxygen vacancies are trapped by kappa to form defect dipoles. After cooling to room temperature, now the main state appears. But there is no correlation between spontaneous stage. During the aging process at 80 degrees C, the oxygen vacancy moves to the first nearest neighbor oxygen site to come up, making the defect dipole direction parallel to the bonding polarization in each domain. So as a result, we can obtain this type of heat-free loop. On the other hand, during the defect formation annealing with here higher than 400 degrees C, oxygen vacancies are knocked up by kappa. Therefore, defect dipoles cannot be formed. After 1 hour aging treatment, those small amounts of defect dipoles might be formed by the migration of oxygen vacancies. Its content is very low. As a result, the single P hysteresis route can be obtained even after the aging treatment. To summarize, the thermal stability of the defect dipole is described in this phase diagram. Above 400 degrees C, defect dipole is not stable and disappears by the dissociation of oxygen vacancy from kappa. But on the other hand, below 350 degrees C, oxygen vacancies are promptly dropped by kappa ion, and a high content of defect dipoles are generated. And also to evaluate the stability of defect dipoles under repeatedly applied external electric field, an electric field fatigue test for kappa 1000 low current tightening ceramics was carried out. This figure shows the bipolar PE loop of the kappa sample before the fatigue test. For this sample, we applied bipolar electric field with an amplitude of 60 kilovolts per centimeter and 1 kilohertz. And this is the PU property of the sample after 10,000 cycles and 100,000 cycles of electric field application. Though the shape of the PU slightly changes depending on the applied electric field cycles. We can clearly see the pink hysteresis loop. So this result indicates that the interaction between content polarization and defect dipoles is still valid even after 100,000 cycles of electric field application. So this interaction is very stable. However, after 1 million cycles, the shape of the PU significantly changes, and the PU becomes mostly single loop. This suggests that the oxygen vacancy dissociates from kappa ion by applying high electric field repeatedly. So, for practical application, I think the further improvement of the stability of defect dipoles and repeatedly applied electric field is very important. Finally, I will introduce the energy stretch properties of kappa doped variable ceramics with defect dipoles. First, we compare the energy stretch properties of iron-doped and copper-doped PET ceramics. This figure is a bipolar PU of iron 1% doped PET ceramics. The recoverable energy density is 0.34 joule per cubic centimeter at 6 kilowatt per centimeter. And effective relative permittivity is calculated from this equation using the recoverable energy density is to 1300. This value is not so bad, but in kappa dot varying tightening ceramics, we obtained a recoverable energy density of 0.53 joule cubic per centimeter at the same electric field, and the higher effective relative permittivity of 3600 was obtained. In addition, the increase in kappa doping content further enhances the energy stress properties. This is the data of the kappa 1% by 1.5% doped PET ceramics, and this ceramic exhibits a much higher recoverable energy density of 1.11 joule per cubic centimeter at 75 kilojoules per centimeter, and an effective relative permittivity of very high value of 4,500 was obtained. So these results indicate that optimal selection of dopants is important, and also utilization of defect dipoles is quite effective in enhancing the energy stress properties. Moreover, we developed a method to drastically enhance the energy stress density. After forming defect dipoles, we performed a folding treatment. In this folding treatment, an electric field was applied to downward direction, and downward direction to obtain downward polarization state. By aging treatment for this sample, we can align defect dipoles in the downward direction. And this figure shows the P property of the sample after the folding and aging treatment. Because the down polarization state is stabilized by stabilized and memorized by the alignment of the downward defect dipoles like this. This state is restored even after the polarization switching by the application of electric field. So we can obtain this kind of shifted P loop. As a result, a quite recoverable energy density of 1.79 joule cubic per centimeter and a high effective relative permittivity of 7,000 and a high energy efficiency of 89% was obtained. And in this graph, we compare the energy stress properties of various samples. The horizontal axis indicates the effective relative permittivity, and the vertical axis is the energy efficiency. And the data of our sample is here, and the plot B corresponds to the shifted T-stress loop shown in the previous slide. As you can see here, this sample exhibits very high effective relative permittivity and high energy efficiency simultaneously compared with the other previously reported samples. And finally, I will summarize my thoughts. In this study, we found defect dipoles are effectively introduced at intermediate temperatures. And in the case of coupled of current tightened ceramics, defect dipole is stable up to 350 degrees C. And also in the electrical fatigue test, we found that defect dipole is stable up to 100,000 cycles of applied electric field at 6 kilovolts per centimeter. think further improvement of the fatigue property is important for practical applications of this biotite ceramics with engineered defect dipole configuration. And also by controlling the defect dipole configuration, we have achieved a very high effective relative permittivity of 7,000 and high energy efficiency of 89%. This is the best performance of our pump. So my conclusion is that high effective relative permittivity and high energy efficiency can be obtained by utilizing defect dipoles. And this is the member of my laboratory, and I am now organizing my laboratory with Professor Yoshinouchi and Yukana Arakawa. And this research is financially supported by these grants. And related papers are here. A part of data shown in this in my talk is reported in this paper published in PGH Materials in 2022. So if you are interested in my research, please read this paper. Thank you very much for your kind attention.
Thank you, Professor, for your wonderful speech. Now the session is open. Audience can interact with the speaker. Audience, please, you can feel free to ask any clarification or discussion. Yes.
Okay. Thank you very much for a nice talk. Maybe my question is related to the dopants, how you choose it, because you have shown that both iron and copper, they both show this kind of allovalent dopant, but the cycle stabilities are different. So can you please give some more insights on what is happening with these vacancies? And on the next part of the question is like current research areas like memristors, where people are trying to understand if they apply a bias, the vacancies can migrate. So is it something happening in barium titanate as well? Because it's a very well-known ferrous material. Thank you.
Thank you for your question. I'm sorry, I can't hear it clearly, but maybe you asked about the...
Yeah, sure. I will repeat this. Basically, you showed the role of iron doping and also copper doping and the lifetime stability cycles. Here, what is the mechanism which makes one dopant to be better than other? Because you are forming vacancies in both the cases. So why iron or copper can be a better situation?
In my research, we got the copper 3' ion.
Yeah.
And to control the valence state of copper, we perform the reduction annealing.
Okay.
And we tried many annealing conditions to control the valence state of copper. And we tried to various copper valences, such as copper 1+, copper 2+, copper 3+. Yeah.
Okay.
Active.
Okay.
And the best performance was obtained for when the copper 3+ is the major defect speed.
I see. Okay. Thank you. I have one more question, if I can ask. This is related to the memristor. Like currently, there is a new topic of using oxygen vacancies as a migrating species when you apply a bias, and that is used for read and write memory. People call it as memristors. And barium titanate being a very well-known ferroelectric material, do you see also a possibility of these vacancies migrating in your bias system? When you apply a huge amount of bias, do they also participate in some of these PE loops, and can you share some insights on that?
Yes, I think, yeah, even in our capability ceramics, I think the vacancies migrate by applying electric field. And this is the reason why my sample gradually performance changes depending on the time. Okay. So if I can suppress the oxygen vacancy migration, I think the performance will be improved.
Okay. Thank you so much.
Thank you very much.
Any further questions? Thank you, Professor Dr. Hiroki Matsuo, for your wonderful presentation. I express my sincere thanks to the organizers of the International Conference, and extend my special thanks to the Department of Physics, SSN College of Engineering, for giving the wonderful opportunity. Thank you very much.
Thank you very much.
Thank you, sir. And it's time to honor the session chair. And I request Anand Babu sir to honor Dr. P.J. Prakash. I request the conveners to also honor participants. Thank you. We'll now break for tea, and participants are requested to reassemble here at the same venue by 11 a.m. And now we can wait for tea. And there's a small instruction. Participants who haven't registered are requested to register at the registration desk. Okay. Thank you.
College. Over to you, ma'am.
Thank you. I'm Dr. Nadu, heading the Department of Physics from Sri Venkateswara College of Engineering. I'm glad to chair this session. So I'm introducing today's speaker, Dr. Surendra B. Anantharaman. He is Assistant Professor from the Department of Metallurgical Materials Engineering from IIT Madras since May 2023. His current research focuses broadly on strong light matter interaction, light emitting devices, energy harvesting system, and spin charge injection in perovskite optoelectronic devices. Before joining IIT Madras, he was a group leader for perovskite optoelectronics division at AMO GmbH, Aachen, Germany, and postdoctoral researcher at the University of Pennsylvania. And he also had a stint working with Taiwan Semiconductor Manufacturing Company, Taiwan, in Thin Films Division before joining the. We will be glad to hear the expertise from Exciton polarons for enhancing the efficiency of 2D perovskite solar cells from you. Over to you. Thank you.
Okay, thank you, ma'am, for the kind introduction, and also I want to thank Dr. Anand Babu sir for inviting me for this nice conference. And I'm happy to be here in SSN again to see you all. In today's talk, I will present something about what is Exciton polarions. Maybe like you have, since this is a physics department seminar, I can go a little bit deep here to say what Exciton polariton is. And you might have heard a lot of this on solar cells, right? This is not a new term for you. You know that the solar cell which converts light into electricity. And the term before that is a 2D perovskite. Have you heard this term 2D perovskite before? No? Okay. Yes? Okay. So 2D perovskite, I will introduce what is that and why we are using Exciton polarons. So now the outline of my talk is just going to introduce about my group where we are working on different materials. So start with 2D materials. You might have heard this term graphene, where we have like one layer of carbon atom and we can exfoliate that. And from there people try to understand what happens to the optical properties. Now if you take graphene, it doesn't have a band gap. Now people started looking into other materials which has band gap in a 2D form. And that is what we are looking into in this system, which is called as transition metal dichalcogenides. And a counterpart of this system is also like a 2D halide perovskite. I will give some more details in the next slide. What is a 2D halide perovskite and why we are looking into 2D material. And also there is also something called as metal organic framework, which is nowadays used for a lot of application in sensors, catalysts, and also in batteries to an extent. And then the next part of the work is like once we have these material, we want to look into what happens to this material in a cavity. So that is what the today's talk is focused towards. Once I have a material and I bring a cavity, what it does to the system. And also we are looking into devices, for example, like photodetectors and also lasers, which we are currently focusing on. Now, the outline of today's talk is about 2D perovskite. So we call this as like rhodesian copper perovskite. Now, this is one of the class of a material where in a perovskite you have listened to the previous barium titanate was a perovskite material, right? So in this case you have barium, titanium, and oxygen. And in a similar fashion, if you replace oxygen with some halides, for example iodine, chlorine, or bromine, you will end up into a new material which is called as these kind of perovskites. And these perovskites have smaller band gap. So compared to barium titanate, which has a larger band gap, these materials have smaller band gap, so you can easily use them for solar cells. Okay. Now when you have a smaller band gap, which means like it absorbs to a longer wavelength of light. Okay, E is equal to hc by lambda. Now that is what this perovskite is doing, but there are some challenges. Now this perovskite has some kind of a 2D stack. I will show you what it does. And now the next thing is we want to put in a cavity. The cavity is nothing new. For example, every day morning we have seen a mirror and then like we have seen a reflection of ourselves, right? Now if you make a cavity for a metal, for a material where it reflects light, for example you can take a thin gold plate and then if you put this material in between like this, what happens when the light reflects back and forth? Does it do something to the material or it makes something worse in this case. So that is what my today's talk is to focus on. And from there we will see how this is useful for devices. Okay, so coming back to this introduction, so the 2D perovskite is nothing but you can see there are like some boxes which are like octahedral layer. So this octahedra has a lead atom in the center and then it has iodine in the corners. So you have like 6 iodine atoms shared with one central atom of lead. Now if you keep repeating this stack 4 times, that is like 1, 2, 3 and 4, then you can call this as one of the class of a 2D perovskite where you have like 4 layers of lead iodide. Okay. To compare, if you take a 3D material, it says like you have infinite order of this lead iodide. If you confine them to 4 layers, that you can call as one of the 2D material. And from there, you can also reduce the number of iodide layers. So you can go to 3, 2, 1 and so on. So now what we are doing here is, this is actually the practical example of a particle in a box model what we write. Right? Where we say like E is inversely proportional to L square. Right? So now in this case, your length is nothing but this number of layers of lead iodide. As you reduce the number of layers, the length of the box decreases, so the energy will increase. Right? Now that is what we are doing here. By decreasing the number of layers, we are increasing the energy. Now why we are doing this is because the next layer above is this organic shell. Now this organic shell is something like which protects the lead iodide from degradation. That is why we are going for 2D perovskite compared to 3D perovskite. In 3D perovskite, there are no organic ligands. There are majorly like very few methyl ammonium molecules which are not so stable or stabilizing the perovskite. So we have to deposit a 2D perovskite on top of a 3D. That's what currently people are doing. But then we started looking into this question, why not just use 2D perovskite? It's already stable. It can give a similar efficiency of solar cell, whatever the 3D perovskite is doing. And that is where the catch is. Now once you start reducing the size, you can probably say like this is going to be the most stable because you can see the amount of organic ligand to the inorganic is very high here. Right? Now if you take such a system where I have given an equation from a particle in a box that you will start increasing the energy as you reduce the box length. Right? That is where the problem comes in. You can see the absorption is going to increase as you decrease the number of layers. Right? This value of n means n is equal to 1, which means like 1 layer of octahedra. Here you can see that the band gap is increasing. The absorption is going close to 500 nanometers. Now if I want to compare with the 3D system, the 3D perovskite absorbs somewhere here close to 800 nanometers. Now how I am going to balance this gap? On one side I have a 2D perovskite which is absorbing very strong, but it has a large band gap and it is also very stable. On the other side I have a 3D perovskite which is currently used in the devices and in fact like moved on to a market scale product, but they are very unstable. So the stability is a major issue here, which the device will start degrading in a couple of years. So that is what we are trying to look into to fill this gap by using one of these 2D perovskite as a case study, and then we will tell whether we can apply this for all the perovskite in this family. Okay, so that is where the optical cavity comes into play. Now what is an optical cavity doing? As I said in the beginning of this talk, you have an optical mirror which is just going to reflect your face, what you are seeing there, and you will see a parallel mirror image of yours. Now the same thing happens when you put a semiconductor within an optical cavity. This optical cavity is nothing but your gold plates, where you can start shining a light that oscillates back and forth because the light is trapped. Now this light cannot leave the cavity, so it keeps oscillating back and forth, and at some point it starts hybridizing with the material. Now this is what we call it as hybridization. This is not very new for you. You might have seen this from a carbon-carbon atoms bringing together to form a molecular orbital, where you bring like 2 carbon atoms, you let them hybridize, you call them like bonding state and anti-bonding state, right? Then you will have 2 new states. That's what we call it as sp hybridization. The same thing we are doing here. Instead of 2 carbon atoms, imagine that one is your semiconductor, which is your perovskite, and it has a band gap. So that is your one case here on the left side. On the right side is your mirror, where your photon is in resonance with the cavity. The light which is going back and forth with the cavity, that is the one which is going to be stable here. And now these two starts interacting and finally it leads towards a hybridized state. Now this new state, what you see here is like there is one energy level above the band gap of the semiconductor, but there is also one energy level below the band gap of the semiconductor. This is what we are going to tap now. That these cases are used for mostly to study Bose-Einstein condensates or lasing, where people want to explore the low threshold lasers, which is also one of our group research activity. But we want to say that this absorption, what you have here below the band gap of a semiconductor, can be useful for stretching the application, or where you can expand the absorption to longer wavelengths. So that is what you can see here, the splitting, which is basically like how strong the light is confined. Okay. Now if the splitting between these two levels, the energy difference is very high, then it means you have a lot of photon interacting with your material. If it doesn't alter at all, if that difference is almost zero, then you can say that the photon is weakly coupled. The reason why we say strong coupling is that light is actually mixing with the material such that it creates two new states. We can call this as half light and half matter. So that is what we are gaining here as an Exciton polariton. Now, there was a recent literature we published, a review article we published in this domain. You can please take a look. This focuses mostly on the devices. So we have thought about a lot of possibilities of using this kind of phenomena in devices, from photodetectors to LEDs and lasers, and even on solar cells. So you can please take a look where we have looked into different polaritons like plasmon polariton. It's basically like the cavity is made up of gold. Then you have gold which has like a plasmon particle. Plasmon is nothing but your free electron cloud, which is around the gold metal nanoparticle that interacts with your semiconductor. Or if you make something like an exciton cavity, which is like your exciton reacting with the light. So for today's talk, I will just focus on this exciton polariton based system. And then this is how a structure will look, where you have a semiconductor, and then you have placed two mirrors on the top and bottom. So this one is one mirror, this is the second mirror. But then what you are seeing here is like different contrast of like magenta and then yellow. These two are different oxide based material. You have to deposit TiO2 and SiO2 such that they reflect and then they finally confine the light within the semiconductor. But that is where the challenge is, where you can deposit the bottom electrodes happily, and then you put your perovskite, and then once you put your topmost electrode, which is oxide, that will degrade the perovskite completely. And that is where the real challenge comes in. You cannot use such kind of a cavity directly for device applications. Now the next part of challenge here is that you need to put some electrodes. This is just an optical cavity, right? Then you want to electrically connect something to make a photovoltaic cell work here. And here you can see that these electrodes are also to be integrated within this cavity, which already complicates your device structure. Okay, so it is not so simple as we thought, that we can take a material and place within a mirror and then find some beautiful phenomena there, but it's really challenging from the engineering perspective. So to make that very simple, we tried to look into a new design where we said that we will take a gold substrate and then we place a semiconductor on top. Now what is this gold doing? This is one of the mirror which is reflecting from the back side. Now we take a very thick semiconductor which acts as a own reflector. It absorbs light. Then once the light passes through this medium to the end of this gold substrate, it gets reflected and then it again gets reflected within that perovskite. So we are just going to use a perovskite stack for two reasons. One is, if you remember the first data I showed here, that it has a very sharp absorption, right? At the same point, it also has a very high refractive index. So the refractive index is something how much of a light can be bent into the medium. Right, now if it has a high refractive index medium and also a high absorption, you can see exactly at the peak where the absorption is there, the refractive index changes. Which means if the refractive index changes around the absorption point, your light or the wavelength of photons which is coming around that exciton will also bend into the medium. So that is what we are doing here, to take the advantage of the sharp resonance beam, which is particularly there in 2D material or one-dimensional nanowires or even quantum dots. We took that as an advantage, and then also when you cleave these layers, these are all like van der Waals gap material. So if you exfoliate it, it will cleave exactly at the van der Waals gap. So you don't have any atomic roughness here. Atomic level thinness will be there. There won't be any roughness such that the light will scatter out. So these are some things like which you needed for a typical mirror. When you want to make a metal to be polished like a mirror, you will ask the guy to polish it so smooth that you should be able to see your face, right? Which means you are reducing the roughness. So that's what we are doing here. By using the van der Waals force, we are exfoliating it where it is cleaving exactly at the bond end, wherever the van der Waals bond are there. Now that is done, and then we got this kind of a stack where we kept the perovskite, and now we want to find out whether light is confined or what is the Rabi splitting value. That will tell you whether the light is confined or not. The higher the Rabi splitting, the higher the light confinement in the medium. Now here, if you focus this perovskite, what we have shown here is RP1, which is one layer of lead iodide. The star mark is all made with cavities. Here people have placed this with the DBR, and then they have found that the Rabi splitting is almost close to 200 millielectron volt. In our case, when we just took a gold substrate and placed the same 2D perovskite, we got the Rabi splitting up to like 500 millielectron volt. So the Rabi splitting is almost 2 times than what you can get it with a simple cavity, or your external cavity is not required here, and you have a very strong confinement of light within the medium. So this is the first step to tell you that this is a new device architecture which you can start working on by placing a perovskite on a gold substrate and then making it to support Exciton polaritons. Okay, now once that is done, we got some insights like, okay, this is forming some new cavity, but then the absorption is like very small. For example, this is an excitonic peak where it is absorbing. As I said, I want to extend the absorption range, right? If I take a 2D perovskite of RP1, which is close to 500 nanometers, my polariton peaks are just close to 525. It is not going up to 800. Okay? Now, what is the next step to do from here to fill the gap up to 800? What we did is, if we start increasing the thickness of this perovskite from 100 nanometers to 500, then there will be multiple cavities. So the light will be reflecting every 100 nanometers, and it will generate new state. So the mechanism is something like this, where you have the first cavity that has an exciton with certain thickness, where your light is reflecting and interacting. And then now if you increase the thickness of the perovskite, you will have a cavity which is off resonance, which means the light doesn't reflect exactly at 100 nanometers, it gets reflected at 150 nanometers. Now that is not bad because it will still form a lower polariton, which will still be lower in energy than this state. Okay, now what we are doing here, we have this state in the beginning and then we increase the thickness to get something new, which is slightly lower in energy than this one. So this is what we did here to find out that when you increase the thickness, the absorption of this peak goes from 500 to 700 nanometers. So you can see a lot of dips, which is all making due to the lower polariton, what you are creating in the device. And then these dips corresponds to absorption. Basically this is like reflectance. Now if you want to calculate the absorption, this is just going to be 1 minus R. Then you will say that your absorption is not limited to 520 nanometers, it goes up to 700 nanometers without doing anything. We have just taken the perovskite with a slightly little higher thickness of 500 nanometers, and there we got these new peaks. And these are not like photonic peaks. One of the reasons where this community stops here is that these are half light and half matter, which means it will have an exciton, but we don't know whether that will emit or not, right? So if it is a photon, it will just oscillate back and forth and that light will come out. But here we try to do an emission study, which means like you create an exciton by shining a light, such that the exciton is created by transferring an electron from valence band to conduction band, and that conduction band dictates where this light has to recombine. Right. Now if I have just 2 states, then you are getting an excitonic emission coming out from the system. But if I have multiple states, which is going to be created by exciton and lower polariton 1, 2 and 3, then each state will have a possibility of emission. Right. So that is what you are seeing here, that each state, whichever is creating an absorption, is also giving rise to an emission. So now there are 2 things clear. This new state, whatever you are starting to observe here, is just not only a photonic state, it is an exciton polariton state, and you can also transfer energy from one species to another. Okay, so I will just quickly go to the next slide and say like, now once you have these states, the next thing is we want to get a device over them. How will you contact them? Because you have these exciton polaritons, you need to collect them as free charges, right? Your photovoltaic device or solar cell is nothing but you have free electron and hole moving out of the device, and that's when you generate electricity. Now, how will you confirm that this material is going to generate electricity? It's just by placing a graphene layer on top of this perovskite. What is the graphene doing here? Graphene is basically a semi-metal. Now, semi-metal is something like having a work function very close to the band gap of your semiconductor. Now, once you have that, you have something like a metal semi interface. When you create an exciton in a semiconductor, this exciton will transfer the charge to the graphene. And then you will see that the photoluminescence will drop because your exciton is not going to recombine in the semiconductor. It is going to transfer the electron to the neighboring graphene, and as a result there is no electron possible to recombine, such that the photoluminescence decreases. So that is what you can verify here by placing a thin layer of graphene on top of this perovskite, and then we try to collect the photoluminescence mapping. Photoluminescence is nothing but you create an exciton by shining with this there, and the conduction band will tell you whether it is recombining radiatively or non-radiatively. Now what you see in this figure here is that around this areas wherever there is only perovskite, you see a light coming out from the system. That is also from the polariton peaks, what you have here. Now when you place the graphene, you can see that the intensity drops significantly. So which means major part of the exciton polariton are transferring the charges to the graphene layer. Now once it is there in the graphene layer, you can extract it by placing a top electrode, and then your device is complete. Okay. So now what we are showing here is a very fundamental device structure where you can just take a gold, place your perovskite on top, and then you place a few layer graphene on top of it, such that your generated exciton polaritons will transfer into free electron holes. And as a result, you will see that there is going to be a photovoltaic device. So with this, we started looking with 3 of my students in my lab, where we want to make a device out of the system. What kind of devices? We want to just make sure that it is going to replicate the previous idea, that you need a back electrode which is gold, which is going to be 100 nanometers. On top of that, immediately you want to have a perovskite. So that's what the concept what we had. And here is what you see, a gold electrode with just a thin layer of spiro. Sorry, it's not readable. So spiro is basically a whole conducting layer. On top of that, we have a 500 nanometer thick perovskite, and then we have an N-type collector which is Diode and ITU. Now this is the same stack what I showed you before, except this top piece of layer. And now when you shine light from the top, it gets reflected at this point and then it goes back. Now once it does that, it starts hybridizing with this exciton, and then it forms a polariton. Now you can see the band alignment, which is also very critical here, because when you want to just extract the electron on hole, you cannot place any material next to it. You need to have some kind of condition satisfied. For example, your electron layer, the conduction band of Diode should be lower than that. It takes the electron from the perovskite, and you should also have a valence band or the homo-LUMO level of the spiro to be slightly higher than the perovskite level. Now once you do that, you can imagine that once you have an exciton polariton, where electron is sitting here, the electron goes to the Diode and ITU, and then the hole which is from the perovskite, it goes to the spiro and then the gold. So now this is a simple device stack what we got, and then we can say that the absorption is also tunable. For example, in this device, when we kept the perovskite as 20 nanometers, you can see the black line is sharp, close to like 600 nanometers. That is what the excitonic absorption of a RP3 perovskite. Now once you start increasing the perovskite thickness, we can see there are like 2 new peaks which are emerging. For example, this case of 500 nanometers, we can see there are 2 absorptions which are coming below the band gap of the perovskite. Now once that is done, we try to calculate how much of light is absorbed in each layer. For example, in this case, you can see where there is only like 50 nanometer perovskite, almost 90% of the light is absorbed by the perovskite. So the passive layers, whatever you have, like your spiro or your Diode layer or ITU, is not absorbing light. It is just only the perovskite that is absorbing light. And once you start going to the next layer, where you have this ITU as a bottom electrode, and again here the perovskite is roughly like 500 nanometers, you can still see this green line is perfectly coming from the perovskite. Only the perovskite is absorbing the light. The other layers are not having any electric field into the system. When you go to the third layer, you can see that these peaks are getting very prominent, and now there are like exciton polariton peaks which are absorbing up to 900 nanometers, and then these green lines are perfectly coming from the perovskite, and this black line is the overall absorption. So if you compare this device stack, you can see compared to the overall absorption, your perovskite is absorbing close to 90% of the intensity. Just 5 to 10% of the light is getting absorbed by the bottom gold layer or other passive optics. So this is very important to find out whether the perovskite is absorbing light or not. Now once we did that, we tried to calculate the device efficiency. So to start with the very thin perovskite, we got roughly like 16%, but I would suggest like we have to compare the stack 2 and 3, where in the stack 2 we have only like ITO substrate in the background, which is just giving you a very weak light reflectance. That's why you don't see a sharp peak of polariton, but you can see there is an improvement from 16% to 19% of efficiency. Now once you replace this ITO with a gold electrode, you can immediately see the efficiency jumps up to 23%. So this is just one of the proof of concept where you have a semiconductor placed between two cavities where the light is just reflecting back and forth, and finally the light is hybridizing with the system that makes the absorption tuned from such kind of 600 nanometers up to 900 nanometers. So here we have not considered any role of doping here. People typically introduce doping or alloying to stretch the absorption band, but doping introduces other challenges. For example, when you want to allow the charge to travel, it gets scattered by all these dopants. So you cannot rely completely on dopants to do the job in terms of absorbing the light, but rather you should just focus on a simple device stack here. Now to summarize this talk, I just finished with this one point, saying that light confinement only in the perovskite has been concluded here, and the other wavelength also it has light absorption only in that stack. So with that we can also say the efficiency, whatever you are seeing here, has been improved from 15% to 23%, and we have filed an Indian patent based on this result, and we are looking forward to submitting a manuscript also in this topic. So with that I will conclude saying that Exciton polariton is also a new way of using them in optoelectronic devices. So far people have looked into mostly in lasers, but here you can see there can be more than lasers. You can look into solar cells. And if you check our review article, we have submitted more information on how we can use them in photodetectors. That has very good fast responsivity also. So in the future we will be looking forward into photodetectors as well. And I thank you for your kind attention. Please ask any questions here.
Thank you, sir, for your valuable points on this, and also thanks for completing in the stipulated time. Hearing.
Yeah.
Sir, we add one more metal on that. Is it possible to increase the efficiency?
One more metal. Yeah, because you will have both cavities to be more reflective.
Yes, sir.
So somewhere like we want to deposit something like a transparent silver electrode, which can be like low cost, but at the same time it can also support some more reflectance than ITU. That can be a replacement.
And
Yeah.
one more point.
Yeah.
You said the one layer will give the higher efficiency.
No, actually like what I said is like in this device, this one few layers, whatever we have put like perovskite, it has the highest absorption, very close to the
So, instead of that, we can use different.
Yeah, library.
Yes.
But when we check the N-type or P-type material, there is some, we can start the device from ITO, deposit TiO2, and then after we anneal this, we can put the perovskite and then thermally evaporate molyoxide and gold, which is possible.
This
No, if you have one, you can.
Yeah. I have one question. That when you were telling about 2D perovskites, it is a large band gap and then it is highly stable. But what about the band gap in 3D perovskite, and which you suggest, either 2D or 3D?
Yeah, in 3D there is already like a band gap very close to, like the absorption close to 800 nanometers, but the 3D perovskite is unstable. So what people are doing now is like there is a lot of encapsulation used, and also the other problem in 3D perovskite is like the ion migration. The ion perovskites, like RP3 and RP4. Then it is possible to use that inbuilt field to split the excitons.
Thank you.
Thank you, sir. As there is no questions, we'll conclude the session.
Thank you so much.
I now request Dr. N.R. Sheila to kindly present a token of appreciation to Dr. Surendra P. Anandaraman.
We'll move on to the next session. Dr. Rajkumar Ramamurthy. So I'm glad to introduce Dr. Rajkumar Ramamurthy, who is an assistant professor at the Department of Physics at Anna University, Chennai, with extensive expertise in experiential nanoscience and material engineering. His research primarily focuses on nucleation and growth processes of nanoparticles, non-classical crystallization pathways, and structure property relationship in nanomaterials and glasses. Dr. Murthy completed his doctorate in the year 2013 from University of Hyderabad, where his work explored the correlation between structure and optical properties of rare earth-doped glasses. Following his PhD, he pursued multiple postdoctoral research positions across leading European research institutions in France. Dr. Ramamurthy has extensive experience with advanced characterization techniques, including X-ray diffraction. He has also served as a principal investigator at major international synchrotron facilities such as PSA at Switzerland, Petra, Germany, Solel at France, and ESRF France, highlighting his strong involvement in large-scale experimental research. He has published numerous high-impact research articles in reputed international journals. Dr. Ramamurthy is also an active academician, apart from researcher. His achievements include prestigious fellowships such as Marie Scotland Curie co-founded Eurodale Talents, fellowships and awards like Best Poster Award in the International Symposium and Industrial Crystallization at Germany during 2021. Through his research, teaching and service, Dr. Ramamurthy continues to contribute significantly to the field of nanoscience and material physics. Now over to you, sir, to present a novel pathway to gold crystallization.
Metal nanoparticles like cobalt, gold, ruthenium, and to gas hydrates, which is shown here. So this is the main energy resource problem currently. So whenever you send the gases, so because of a different thermodynamic condition, you may end up with forming a gas hydrates. So that would lead to blockage in the pipes. So to understand this, I need some in situ tools as well the different characterization techniques like from lab techniques like optical microscopy, X-ray diffraction to synchrotron facilities like small angle X-ray scattering, X-ray absorption spectroscopy and so on. So today I present the crystallization of gold nanoparticles mainly using the techniques X-ray absorption spectroscopy, X-ray scattering. So this work is possible with a group of very nice people. So they belongs to mainly from France and one from USA. So he's a Valery Pitko. He helped us to treat the proton scattering X-ray diffraction data. So let's start with crystallization. So what is crystallization? So anyone can tell you, have you seen any crystallization product in your life? Any crystallization product?
Sugar, sir.
Sugar, okay. Anything else which you commonly observe in your daily life? Salt, okay. So nature is a very kind thing, so it can form many crystals. Like when we have an cold day, we have ice stones, right? So that's the product of crystallization. And we see a named wood chip. So this is the spines is there, right? So whenever the spine is gone out, so it is able to reproduce by itself. It's a calcium carbonate again. So then, as we found out, sugar crystals from honey. So then the gas hydrates that I was talking. Then the lab-grown nanoparticles, which is mainly evolved by a crystallization process. So how to summarize crystallization? So crystallization is something, so especially I'm focusing here on bottom-up approach. So whenever we form a crystals in a solution, so it starts from atoms or molecules and then it's going to stack periodically and then transform into a crystals. So the crystal is going to be from nanometer size to long crystals. So if it is infinitely periodic, we call it as a bulk. So how this happens? So whenever we want to form a crystals in our lab, so we say that I want to start with some concentration of precursors dissolved in a solution. That's what we do, right? So that's what the common term existing in the lab. But what is the driving force to form a crystals in our lab? So this going to do in our synthesis? For instance, so if I'm going to have amorphous nanoparticles, so what is the surface energy it's going to create during the nanoparticle formation? So that is the main question. So here the assumption is, so that is the main question. So here the assumption is, so the surface energy is the boundary between the solution what we have taken and the nanoparticle surface. Whereas here, the boundary is not a solution and the amorphous solution. So in that case, I'm going to change my surface energy, right? So in the droplets case, we have some concentration that we have not taken. So either it's undersaturated or highly supersaturated. So in that case, I'm going to have different CPs. So again, different chemical potential energy driving. So as a result, we would expect a different RC and different nucleation rate. So that would misguide us. Whenever we take some concentration, we cannot predict what we have at the end. Whether it's a small or big particles, we cannot directly predict. So we need the pathway a crystal is going to do or take. So these are the challenges we need to understand before predicting how to control the size of a nanoparticle. So to understand this, I've taken a model system, gold nanoparticles. It's interesting for application and fundamental perspectives. As you know that ultra small nanoparticles can be used for bioimaging applications. The thin nanowires can be used like Dr. Surendra was pointing out the photonic applications where the light can be penetrated deep into the gold nanowires, which is act like a transparent connecting electrodes. And the gold nanoparticles we can have a 5-fold symmetry, which is not common in the bulk. So this is existing in the small size nanoparticles. So here we synthesize gold nanoparticles by reduction process, as many of you do. But here we have done at room temperature and in Exciton. Exciton is a harmonic medium where we cannot readily dissolve this ionic species in it. So to assist the dissolution, so I need a long chain polymers. What we have taken is polyamine. So these are the structures of different precursors I have taken. Gold precursors in Exciton with the help of polyamine. I start introducing the reducing agent. The reducing agent is trihexopropylserine. So once I added the reducing agent, so the H the electrons and start the reduction process. So as a result, we end up with ultra small nanoparticles of about 2 nanometer diameter size gold nanoparticles. So after synthesizing the structure of the system. So that's what we have done. So this is not a regular X-ray pattern, it's a regular, but I have shown here not in a conventional way. In a regular pattern, you always have a 2 theta against the intensity, but here I have shown Q. As you are all familiar from the solid state physics, the scattering vector is nothing but the representation of 2 theta. Okay? So the scattering vector as a function of intensity I have plotted here. So the red is the exponential curve and the blue one is the reference curve of a gold FCC. As a gold, they always exist in FCC structure. So here I am going to compare, and I found that the peak positions are not in matching with the reference data. So we conclude that the nanoparticles that we have synthesized is not a FCC structure. So to understand the structure with the help of a Valedictory, so we have done a modeling on this data, and then we try to simulate this one, and then we match the experimental and reference one. So this is the pair distribution function. So from this we have to Fourier transform and reach the pair distribution function. The pair distribution function is nothing but the correlation between the 2 atoms which is present in the system. So if I am going to have the correlation, this length is approximately equals to the correlation between the atoms from here to here. So that's the correlation. Correlation shows that we have a icosahedral structure instead of FCC. So now I want to understand how this nanoparticles is going to reach this size. So before showing that, I will show some complications. What are the challenges we have to understand this? So I'm going to show that I'm going to add the reducing agent, triisopropylserine. So this is the gold precursor. So this is some pale yellow color. So I'm going to add it. So here's the video. No, I have a video also on this.
C'est le continu à part. Notre solution. Et le continu apparaître de notre
So I
solution.
have added it. So you see there is a color change, right? So we are seeing there is a change in physical appearance, right? So what is the indication of the physical appearance indicates? So something is changing, is happening in the system. So the color, it indicates a light blue or a kind of brown or like dark brown. So the dark brown is the color of a gold nanoparticles. So you see how long it took to form a gold nanoparticles. It's a fraction of a second, right? So will I be able to characterize this formation at lab facility? So for instance, I want to take XRT, so I have to wait for 30 minutes minimum or 20 minutes to characterize it. So before that my reaction is over. I cannot follow this pathway. So if I want to capture this efficiently, so can I go back to the slide? So what I have to do? So I have to follow the formation in a live environment. Do I have to do that? Yes? You all agree? Yes. So I have to follow this. So I have to follow this. For this I have to construct a certain chamber such that the synchronously as the reaction evolves. So that's what I am going to show in the next slide. So then here we have the another thing. So the reaction is about fast, as you said, it's a few seconds. So then we have some complex pathway, so we don't know what are those sizes. So those are the things are the challenges. So the reaction evolves less than a second, and we have a pathways which is having a different complex structure, which is having a size ranging from nanometer to micrometer, which I don't know. So to understand this, I want a characterization technique which is going to capture such a small length scales, nanometer length scales or atomic length scales. So I want to find the characterization tool. Then the second is I want to have some institute techniques that should be synchronized with the characterization. So that's what I have. So I have developed the institute characterization tool. So this is a flow techniques. So where what we do is instead of mixing manually, so I will inject my gold precursor in one side and reducing agent in another side. So this will be controlled from the other place. So when I say controlled, we go to the synchrotron facilities. So we perform the experiment in the experimental batch where we have mounted this setup and we will not inject directly. So we will be ready this setup and then we go to the workstation where we work. So we launch the experiment. So when we launch the experiment will be synchronized by mixing the reaction as well by characterizing the, okay. So this way the reaction will be synchronized with the characterization technique. So we are going to monitor as a live real-time process. So the interest is, so I don't understand what is the pathway. So to understand the pathway, I want to understand what are the structural properties of the system. So at atomic level, I will be using X-ray absorption spectroscopy. Then at nanometer scale, I am going to use small angle X-ray spectroscopy. So the X-ray atomic spectroscopy works on the principles of photoelectric effect, where I send photons, which the atoms we are interested in. So it's going to hit the atom, trying to knock out the electrons from the core level. Then the knocked out electrons travel, and then it will be backscattered by the surrounding atoms. Then the interference will happen. So as a result, we are going to follow the absorption pattern as a function of energy of the photons that we are incidentally. So by modeling these oscillations, so these oscillations carries the information about the local environment. So by modeling that, so I can identify how many number of atoms present in it, around it. Then I will be able to tell what is the size exactly it is placed around it. Then the Bipolar factor tells about whether it is an ordered structure or disordered structure. So to start with, I'll present absorption spectroscopy pattern that shows some peak followed by some oscillations that I have shown in the reference one. So the corresponding Fourier transform shows a peak in the R space followed by flat region. So when you start observing a peak, that indicates that you have atoms which is well correlated from the central atom that you are in, and it is placed similar distance around the center. If you start observing more peaks here, that indicates that your correlation starts increasing, which is nothing but a radial distribution function. Your orderless gets increased. So now what I am doing is, so I am going to add my agent. So that's what I am mixing the reducing agent in the flow chamber. So then you follow it. So before we found that the structures what we have the gold chlorine structure, the gold plus 3 oxidation state. So here process that what is the oxidation state of gold atoms. So this is plus 3 oxidation state. So then we waited for 22 seconds. So we have seen that there is no change till 10 seconds, but we start seeing a small peak at a distance around 3 amps. So this indicates there is a slight change is happening, and also there is a drop in intensity in the first peak. That indicates that the coordination number is changing around the central atom that we are interested in. So with further increase in time, we found that the shape of the peak starts changing, and finally we have reached a shape such that the absorption peak that we have seen, intense peak, is completely disappeared. We have an oscillation that's different from what we started with. So that indicates we have something different product that we have started with. So by seeing the radial distribution pattern, so we are observing more than one peak in the R space. That indicates we are having some ordered structure compared to the initial times. So this indicates that we start with the disordered structures and then it transforms to ordered structures. So the second, so I want to understand the reduction process. So as gold exists in 3 different oxidation states, I want to quantify the gold oxidation state as a function of reaction. So for that, I have done the linear combination approach. So where I have taken a gold 3 reference, the first spectrum, and the gold 0 reference, the last spectrum, and I also prepared a gold 1 intermediate spectrum. So then I have measured it, then I have done the linear combination approach to quantify what is the concentration of gold 3, gold 1 and gold 0 at given. So by doing that, so we found that at the initial time the system is very silent, which is less than 20 seconds, where the gold 3 starts decreasing and gold 1 starts forming. So after 20 seconds, we start forming a gold 0 more and more. As the reaction proceeds, the gold 3, gold 0 formation increases and we have reached gold 0 particles. So with the X-ray absorption spectroscopy, we identified what is the gold oxidation state, and also we quantified what is the order of the system and what is the change in order that have taken place. So to understand the nanometer length scales, so we have utilized the small angle X-rays technique, where we have shined the X-ray source again. Then we have followed the deviation in the X-rays, the scattered X-rays. So here also we plot in a log scale X-ray intensity as a function of log scattering wave vector. So here we will get few information from the small angle X-ray scattering factor. So this is not very new. So in solid state physics you have seen the atomic scattering factor, right? There is an exponential decay. So it's the same. But it contains some more information, the structural correlation. What we have seen is just an atomic scattering factor. What we have is a scattering factor along with structural correlation. So the low Q, I will call this as a low Q, will give the information about the yield, the number of particles that you have produced in your synthesis. And the mid Q, I say the knee position will tell us what is the size of your nanoparticles or nanostructures that you have. And the tail part at high Q will tell us what is the shape of your particles. So if my slope is 4, I would say that the size the shape what I have is a spherical in shape. The size 2 will tell us it is a disc shape. The size 1 will tell us it's a cylindrical shape. So that's what the information we will get. So with this, I'll show the X-ray scattering. So this is the spectrum we always intended to have when ions is dissolved in a solution. But what we have when we characterize a precursor solution, we already have a plateau followed by a knee and then there is a slope. So this indicates that we already have some structures in our solution. So even though it's a disordered, we have some structure. To understand the size and the shape, so we have used this phenomenological model. It's called the Fukushima model. So where this first parameter will help us to fit the low Q part. The second function will help us to fit the high Q part. So with this, we will gather the yield and the size of the particle, and from the slope, we will get the shape of the particle. The very first spectrum without adding a reducing agent shows the size is around 4.4 nanometer in size. So as the reducing agent is added, so as it is consistent with the X-ray absorption spectroscopy, so the signal remains the same. It is not modifying as observed in the X-ray absorption spectroscopy. The size is varying around 4 nanometer. So upon increasing the reaction time, as you see that the knee is shifted towards right. So the shift indicates that as you see in the X-ray diffraction. So the shift in the theta that indicates the shorter distance or longer distance. If you go for higher thetas, it's going to be shorter, right? So this indicates that we are going to have, we start with the big structures, which is around 4 nanometer. Then it it goes to a smaller size. It's around a 1.8 nanometer. Then it starts growing as a function of time. Then we have a further shift in the mid low Q, and then we end up with around 2 nanometer size. So by comparing both small angle X-ray absorption spectroscopy, we can conclude that. So we start with some clusters. We call it as a pre-nucleation clusters, since this is forming before the nucleation process. So they are in this sort of X-ray absorption spectroscopy. Then it starts forming a one below the 20 seconds. Then it transforms to a crystalline gold nanoparticles. Our system shows that gold nanoparticles doesn't follow classical nucleation theory. So it states that it is not directly transformed into crystalline nanoparticles. It is mediated by the intermediate states called pre-nucleation clusters, and then reach the final nanoparticles. Clusters, and then reach the final nanoparticles. So that's the conclusion. So what is the take-home message? So understanding the pathways are very essential. So the understanding the pathway will describe what are the intermediate states. By understanding the intermediate states, we will be able to understand the thermodynamic conditions, what the system is having. So from there we can go and predict what is the recipe for designing the final nanoparticles. With this, I conclude. Thank you.
Thank you so much for your wonderful session showing the right way for gold crystallization. The forum is open to you all for questions.
So thank you for the wonderful talk. So I'm new to this field, so I just want to know. I just want to know, you were talking about the path correlation function, right? So how do you experimentally measure?
Experimentally, we try to record a data, like I was showing here. So here what we have done is it's a total X-ray scattering. So we use a high X-ray source. So the Q range what we acquire is very long compared to the X-ray source what we have in the lab facility. So with this we will record for high Q ranges. Then we Fourier transform this signal. So from this we will be obtaining such peaks. So these peaks are indication that we have a correlation. So this we cannot directly tell us what are those peaks are corresponds to. So if I want to understand what does this peak corresponds to, I have to do a simulation. So that simulation I have to compare, and then only I can conclude what are those peak correlation. I cannot directly conclude from this. I need a simulation data.
So you can only infer from that data.
Yeah, so that info, what I can infer is there is a pair correlation which is existing over a range till 20 angstrom or 2 nanometer. That's what the information. But to pinpoint what is this, that's what the information. But to pinpoint what is this, each pair correlation peaks corresponds to, I need a simulation data.
Okay, sir. Thank you.
Any other questions?
Thank you. It was nice presentation. I'm very curious about this setup you have made. Homemade setup.
Yes.
Yeah, you have done in laboratory or?
So this we have done in our laboratory, but when I was working in France.
Okay.
So here I am trying to construct one.
Okay. So what would be the size of this whole setup? I mean, in terms of inch or centimeters?
It's
this size of this whole setup?
The whole setup is not more than 30 centimeters.
30 centimeters.
It can be very small.
And what about the internal part where you are injecting this?
So there is a Teflon tubing. So
Okay.
this is Teflon tubing. We have a T junction. It will be mixed, two solution will be mixed here.
Okay.
Then again the outlet will be connected with the Teflon tubing again. Or any polymer which is not very long. So it's very thin.
So one end you are introducing gold or a chloride solution,
Yes.
and other end you are introducing
Reducing.
reducing agent. So what time you are giving for this to interact to convert into nanoparticles?
So the dead time, what we have is the volume that is going to transfer from the connected the D junction and this probing point. So the dead time is around few seconds, not more than that.
Not more than that.
If it is microfluidic setup, it is going to be like a 300 microseconds. I can start measuring.
Yeah, I could able to sync this one with the microfluidic
we have
setup.
done microfluidic also presented today. So 300 microseconds we can follow.
So for that you are introducing X-ray beam from the top or UV. I think microfluidic setup need UV rays, right?
So for fabrication, yes, we need photons, UV photons.
Yeah.
But for characterization, so once fabrication, the reaction will be conducted. So I have a microfluidic setup also here.
No, not an issue. Yeah. So here you are using X-ray beam, right?
Yes, we use the X-ray beam.
Okay, sir, fine.
But I have a microfluidic setup.
Fine. Thank you.
Yeah.
Yes. You have questions?
Thank you for the nice talk. My question is related to the critical nucleus. So generally we say that in nucleation theory, the surface and volume ratio is going to be a competing factor. And finally you will have a critical nucleus and then the Gibbs energy goes down. Now in your case you see that initially the diameter of crystals are bigger and then it drops, then it grows. Like why there is a drop? What is the driving force there?
So initially we have not a crystalline object, it is a disorder. That's what we confirm from X-ray absorption spectroscopy. So initial structures what we have is a disordered structures. So these disordered structures doesn't contain all the precursors what we have. So for instance, if my final nanoparticles are around the 2 nanometer size, it will hardly take 250 to 300 atoms. So these clusters what we have, it only contains 100 atoms by counting it. So as a result, so these 100 atoms is not only a gold atoms, it is also a combination of water molecules that we have in the precursors. So these clusters makes a big one. So once this left out things goes out, so then we have this shrinkage. So then only we start forming a gold crystal.
Basically a different species or
different species, yes, different species. It's not a gold precursor. Gold alone, yeah.
Thank you.
Yeah.
Yes. Okay, thank you, sir. We'll conclude the session.
Now I request Dr. A. Chandrasekharan to kindly present a token of appreciation to Dr. Rajkumar Ramamurthy.
Next, we'll move on to the session. Applied Sciences, Auditorium University. Previously, he worked as associate professor at the Department.
Physics and the materials, those aspects. I'm going to share something different about applied chemistry concept as well as the material chemistry concept that will help you, some of the young scholars from different colleges, universities who are working in experimental physics basically, right? So I think I will start with the introduction and I will skip off, right? So I hope you would have come across this one, the functional materials or device or any system with a controlled manipulation of a material. He fabricates some materials in a controlled manipulation which has different properties and different extreme material and different properties will be arised when you fabricate probably 1 to 100 nanometers. So if you prepare such materials, probably 1 to 100 nanometers. So if you prepare such materials probably you will be ending with different novel properties that includes physical, chemical, electrical, mechanical, optical, and different properties, right? Basically, nowadays in nanotechnology, final application. If you take people from nowadays in nanotechnology, final application. If you take people from life science, they use nano gel or nanoparticle for drug delivery applications, right? So it depends on how you want to use nanomaterial for your end application. That actually shows this one. And why this is important? Because of 4 important unique parameters, which is actually nano size scale, large surface area, lightweight material, and with high porosity. And some of the nanostructures I have listed here. And you can see here this slide, available naturally as well as synthesized by laboratory approach from macro world to micro world or nano world. So you can see here hair size of approximately 5 mm in diameter, and if you go down to micrometer, you can see here human hair in micrometer size, and further if you go down, you can see here the DNA which is in nanometer size range in naturally available in the system, as well as if you see on the opposite side, meter in size and or polymer nanoparticles or polymer nanocomposites you can prepare. So simply nanocomposites you can prepare, but this method doesn't require any like we have published. I'll share that, and I'll end up due to time constraints. So as you all aware that energy, is a very big threat now also, right? There is a gossip in social media. Fuel is a problem now because of this war, right? Is there any lockdown in global, right? People talk about this, and you would also witness that. Some 10-15 days back, there was a huge people in petrol bunks, right? Shortage of. So alternative energy is there. So if Arab countries, if they shut down this fuel, it actually impacting the globally, right? So fuel shortage. If there is no transportation, no vegetables, no groceries, and everyone will remind this situation remind us the lockdown period, Corona lockdown period. So everyone go to shops, supermarket, buy things for 3 months, 2 months, and there will be a high panic stage, right? So it actually resembles, right? So what we have to think in an alternative way, we have to go for energy, renewable energy, green energy. That's what Government of India also every time says that to plan for e-vehicles, almost cars and vehicles, scooters. You could see here, right? Maybe you think about next 15 years, 10 years, everywhere only this e-vehicle, possibly, right? So we cannot completely remove the petroleum-based vehicles, but it would be 90% or 80% we will be having e-vehicles, right? Because of depletion of fossil fuels. There is no crude oils or petroleum products. So alternatively, we have to go for battery-based, photovoltaic-based, right? Supercapacitor, fuel cell-based, right? So if you are going there, and if you take batteries, lithium is a very expensive material and rare material also. It is very tough to, and people from physics department, they are using sodium-based batteries also nowadays coming up for replacing the lithium, right? So obviously, thinking of alternative energy is very important. So energy is coming into picture because of high usage of renewable natural energies, right? So this graph shows how depletion of fossil fuel is actually occurring. And yes, we have to think of fuel cell batteries and supercapacitor. For this, as a metal people or metal chemist people, we are synthesizing some kind of composite material which has multifunctional applications and multifunctional behavior for sorting out these kind of applications, right? So one work we have discussed here is that method fuel cell. I hope you have studied in applied physics, right? How fuel cell works, right? So the flow chart is given here. So it one part is undergo anodic oxidation, another part is cathodic reduction, right? So it takes place and you can harvest, in terms of energy. Free electron is coming out. You can harvest in terms of voltage, right? So for harvesting these things, we have applied nanocomposite materials. You can ask me what is nanocomposite. It's a multi-phase solid material where one phase has 1 or 2 dimension, less than 100 nanometer. So idea here is why we need to use multi-phase, right? So maybe in another 5 minutes I will complete. So why we have to use a nanocomposite material? If you take that basically composite material, it's the integration of more than 2 materials, maybe 3 materials, right? Or 4 materials even, right? So if you integrate different material in one single system, it actually shows a synergetic contribution. Say for example, you take one material as a polymer, another material as a metal oxide, another material as a carbide. Laboratory approach for synthesizing nanomaterial. It may be a metal oxide based material, or carbon based material, or even polymer based materials. Like next. So with this, next. So I thank our team. Next. So I would like to acknowledge our university for providing basic support. Next. I also thank the funding agency for providing research support. Thank you one and all for your patient listening, and I am happy to answer for your question if you have any questions. Yeah.
Thank you, sir. Audience, if you have any questions, speaker is ready to answer your questions. You can interact with your speaker. Okay. Thank you, sir. We'll conclude the session.
Now I request Dr. N.R. Sheila to kindly present a token of appreciation to Dr. Raghupati Dhanisra.
Thank you.
Thank you to the session chairs and speakers for an insightful session. I also request Dr. G. Anandababu to kindly present a token of appreciation to the session chair, Dr. N.R. Sheila.
Organizer and Chandrasekharan sir for giving this wonderful opportunity of chairing this session on this conference. Thank you.
We thank our speakers and session chairs for their valuable contribution to this conference. The lunch will be provided at the main canteen. Kindly assemble by 2 o'clock.
line system, thin film materials, and functional materials for sensing and energy application. Her work combines experimental and theoretical approaches to study the structural and electronic behavior.
The composition and analysis of the material, like if you're 2s, is it 1:2, or how is it, or it is 1:1.5, or something like that. For that usually we are using. XAS is usually used how to understand the orientation of different molecules, whether a mole is surrounded by 2 sulfur atoms, or whether a mole is surrounded by something else. So this kind of situations. We will be using these ideas to understand those which we will try to understand. So XPS is usually using the lab source, or sometimes we use synchrotron sources also. However, for XAS, we definitely need, right? They will help us to probe the coordination, the spin, and the oxidation states with high resolution, and it also gives you the data in a very quick time, right? And as you see, for the samples with the additives, there is a shift in the peak position, right? So a red shift is observed with the addition of pitot bases, indicating a shortening of the contribution length. How did we find out? We did this from the Raman. We referred to literature. We did some calculations with our groups from the theoretical section, and they told us that it was shortening of the contribution. Fine. Then we looked into the STR part of it, and again we find similar kind of things here. So if you look at the speed of pieces, again, a red shift is observed here. Now, if we go back for the cellulose part, if you see here, for the cellulose part, it remains unchanged. So no shift at all, right? And again, for this is the PVDF with PVP, again another polymer. These are two polymer systems. There is a PVP, right? When I go to the SSN, I find again here cellulose remains unchanged. There is no change in cellulose. Change means what? From the number we said, from the calculations, etc., there is some kind of shortening of the bonds, right? And now we see, okay, in FTI also we are getting similar kind of things. So we try to see that there is some kind of bonding environment change, which means the polymer chains may be getting entangled or may be getting dissociated or something is happening. How do we understand that? So what we did was, we did the Exciton, right? We did a Pro6Ps, we did not find. So 5 star, sigma star, these are all the different kind of bonding and anti-bonding orbitals which you find. So these star bonds are the ones where the electrons are moved from the unoccupied to the occupied state and vice versa, right? So if you see here now, this is the one with PDOT PSS, with PVDF, the orange one is for PDOT PSS, the black one is for the original PVDF, and the red one is for PVDF. Now please look into this one. The near edge that we find here, the peak value of this P1 spectra is 284.8. Please refer to the table here. And further for P3, P4, P5, P6, each transition that we've recorded here, these are the movement of electrons from one shell to the other. Can you recall what we said earlier? That the electrons will be moving from 1s to 2p, 1s to 2p, in P again you have Px, Py, Pz. So 1s to 2p half, 1s to 2p, 3 by 2 like that, it is moving up and down, right? And so all these are giving you different kind of transactions. So these are the different type of transactions that we've recorded, and for every system that we have recorded here, the intensity you can check, it has varied. For PDOT PSS, P1 is quite high as compared to that of PVDF, whereas for PVP it is not that much. This is again the layered structure for the same one. Now, when I talk of this intensity also, that it is higher in case of PDOT PSS and somewhat okay for this PVP, whereas it is very low for the original PVDF. What we understand from this is the transaction that would have taken place between your C11C, which was when we did this fit, all we found was, after this fitting, that this is the best kind of equation which you found that the resultant composite for this was Ax plus B 1 minus x, and we tried to find out the R factor, etc. using this fitting, and our information that we found was perfect. Based on that, we tried to find possible kind of interaction, and we found that between this PVP and PVDF, the oxygen molecule that you have in PVP is what is contributing to some additional entanglement with your PVDF hydrogen atoms and forming some kind of local bonds. Whereas in case of PDOT PSS, we had these oxygen and this was the sulfur, which were bonding with the hydrogen of the PVDF. In both the cases, we found that chlorine did not interact. This again would would give us the information. Chlorine is highly electronic, so it would repair. Whereas in my cases, the additives that we were having here, they had electrons could donate. So definitely chlorine would not participate. Based on this, we could then explain the conductivity studies that we found in PDOT cases, and we could see that as you increase the concentration of the additives, there is an increase in the conductivity and there is a decrease in the neighboring distances of the molecules. So this is how we have correlated excess and XPS, and with that we try to understand this kind of system, and that is what I have to bring out for you. Now these are some other examples. So do I have some more time?
Yes, ma'am. Proceed.
Yes, ma'am, you can proceed.
Yes.
For the next one.
Yeah, so some more examples I would like to give you. I was just mentioning that with XPS we could find the depth profiling, etc. So this was for your polymer again. When we did for the safety medium, what we did was we did some angle resolved XPS and we tried to find out the concentration of fluorine atom from the surface for the whole sample which I showed the XPS on, and we found fluorine was higher at the outer side. This is the outer side that we had, and almost absent as we go inside. So it is at a depth of about 10 to 11 nanometers. So here you find the concentration fluorine quite less. Whereas this is for the hydrogen atoms. Since it was a whole sample, it was more or less like the same value, right? So this was one example. This is again the latest that you have, that now people are also using some softwares to predict the morphology. And this is another example I would like to give you. This is not from mine, this is from an IIT conference website. They have done this exact spectra. I hope the spectra is clear. This is the XPS for N1X. This is a graphite on which Nadu taken the spectra of the sample. Now this is the exact spectra. Please look into the spectra of the sample. Now this is the exact spectra. Please look into the shift in the peak. They are on the same scale. So here your peak for nitrogen is at 404, whereas here the peak for nitrogen is around 401. So there is a clear 3 eV shift between the excess absorption line and the XPS peak position. This indicates that it usually excess is a final state we see. Why? Because XPS is, like as you shine the photons, it will be interacting and then it will release electron, and then it is, as you switch off, the phenomena stops. Whereas excess gives you final state. Like you cannot revert back to your original state. Every time you begin measurement, you will be getting that final state. So in final state, we usually find a neutral peak, right? All electrons would have gone, they would have ionized, they would have released energies, whatever, and they would come back to the neutral state in the X-ray absorption spectrum. So when I have 3 eV, what I can say is, for such difference of energy, I cannot use XPS data to locate the pulse range. Now this is a drawback. So what I should do in such case? I said that we will be using XPS data to find out the excess values and correlate those data. So now I'm finding that using this particular system, since there is such a gap in EV, I'm not able to find it. I need to do what? Other than that, we can do some kind of theoretical studies also. So we can try to find out the 4 goals that are solved from this XPS spectra and from the valence of spectra. Like these areas will be giving some kind of vacancies, information of those, and using that we can do. So directly the XPS is not useful for understanding the exact data, and so I will have to rely on something else. There were some other data like this. This is platinum. This is a commercially procured platinum on carbon, and this is a platinum on cobalt and selenium kind 4-shell structure. So you see the XPS. If you see here, there is a shift in the
These are the table of contents. And in the introduction slide, scintillation in the cesium source these values are nearer to the commercial scintillator and the standard scintillators. So this is the right output of the plastic scintillator. because the light output is high light yield in response to the high radiation response. So light yield of our scintillator, light yield of the scintillator is still beam has a 10,005 scintillator. So as the reference still beam, our light.
And these are the keywords of my topic. As my device is reconfigurable device, it is field world of reconfigurable field. So first I want to say about reconfigurability. So what is reconfigurability? If a single device can act as an entire device or pattern.
Reliable environment where the energy is not an issue. If we are using these two things, that is piezoelectric and thermoelectric, we have sounds everywhere. Even in this auditorium I am speaking and the sound waves are moving towards. If we place some of the diaphragms made of piezoelectric material somewhere in this auditorium, it can capture energy. Though small in these days, it can capture energy and that can be used for some other applications. In case of microelectronics, which we are using in seabeds or in any volcanic activities to monitor something in CCTV cameras, we can use this, and that might need small energy as of now, and if we develop it to
any particular doing?
Yes sir, we are
any particular doing?
Yes sir, we are doing a project for creating an energy harvester which converts this piece of sound energy and heat energy into electric energy.
You also consider the cost. Okay, the thermoelectric and piezoelectric materials are cost compared to the normal available materials. So you should think of that and we will. Okay, thank you. OP14, the next presenter will be OP14. Varun. Okay. Okay, OP15, Rajendran Dhanapal. OP15, Rajendran Dhanapal? No. P16, Venkata Veraprasad.
She's here.
Okay. Sorry, Venkata Veraprasad.
No. Students.
Last one.
Jai Shri.
16.
Guide.
A kind request to the participants, if you are available, please come and up with the front seat so that we can proceed further. And make sure that you are sticking with the time. Any other participants? If you are ready with the PPT, we will proceed. Next OP 17. Tilaka, you available? Yes, then we can.
Good afternoon, everyone. I am Tilaka, research scholar, doing research work under the guidance of Dr. Alumelu Magai, Biotech High-Tech, Dr. Rangarajan, Secondary Engineering College. My research work based on organic, non-linear NLO crystals. Some few introduction about NLO crystals. Organic NLO crystals are huge, attracted interest in past several years because of their non-linear optical efficiency. NLO materials are using in various applications like light modulation, optical switching, medical diagnostics, optical information, and signal processing. Some
sorry for that. Kindly go with the objects, that would be fine.
Okay.
Stop spending time in the introduction. Go with the object.
Okay, just 2 minutes. This is the preparation method of 1:1 ratio of 3,5 trimethyl cyclohexane to malonitrile and 4-hydroxybenzone. These are the two different solvents like methanol and ethyl methyl ketone by slow evaporation technique. Piperidine acetate added to the solutions, and finally 25 days after the well-defined single crystals were armed. The grown crystals are A belongs to crystal grown from methanol, and figure B shows the crystal grown from ethyl methyl ketone. The grown crystals subjected by the following characterizations: single XRD, powder XRD, FTR, UV, frontier molecular orbital, molecular potential, molecular docking, and second harmonic generation. From the single crystal X-ray diffraction analysis, the crystal belongs to orthorhombic crystal system, and the cell parameters are well agree with the reported values. From the powder X-ray diffraction analysis, the prominent peaks are observed, and the peak at 201 and 221 intensity is high compared to methanol. This may be due to the presence of ethyl methyl ketone solvents present in the OH1 molecules. FTR spectral analysis confirmed the presence of various functional group presence in the material like phenol, carboxylic acid, and nitrile and methyl groups. UV visible absorption spectroscopy analysis. The lower cutoff wavelength was found to be 424 nanometer from methanol and 470 nanometer from ethyl methyl ketone, and band gap energy was calculated, found to be 2.9 electron volts, and it's a promising candidate for optoelectronic application. Frontier molecular orbital. HOMO is represented as highest occupied molecular orbital, and LUMOS represented as lowest unoccupied molecular orbitals. And HOMO is donating an electron, and LUMO is donating accepting an electrons. The HOMO-LUMO energy gap was found to be 3 electron volt. In this figure, OH group donating 1 electron, and NC group accepting 1 electrons. Molecular electrostatic potential. In this area, red color shows the negative electrostatic potential, and blue indicates the positive electrostatic potential, and green and yellow usually it's a computational technique is used for drug discovery, predict how a small molecule interact and bind with the proteins. In this case, my material OH1 molecules interact and bind with the protein 6-OA. Second harmonic generations, the single crystal X-ray diffractions and confirmed by the emission of green light from the sample, and is 0.4 times higher than KDP. I conclude here. Thank you.
Okay, you're chosen two different solvents, right?
Yes, sir.
Have you studied anything related to that? Why it shows that change?
Usually, OH crystals reported only in methanol solvents, sir. I interested to two solvents like methanol and ethyl methyl ketone. Methanol is a protic solvent and ethyl methyl ketone is an aprotic solvent. Protic solvents can donate electrons easily, but ethyl methyl ketone solvent lack of protons and it not shares any protons to the compounds.
Have you tried it any aqua solution?
Aqua solution dissolved in the materials, sir.
Then why don't you go for any mixed solvent? You have tried it in mixed solvent, right? Then definitely you will get some different outputs. Since your ultimate aim is you are determining the NO efficiency,
Yes.
that is your ultimate aim.
Yes.
See, most of the aqua solution will give the good NO efficiency.
Next time I will
Then you would have tried with the different
solvents. Next time I will try.
Okay.
Thank you.
Any other question?
Numbered, maybe go for UVs, right? Already you mentioned the optical band gap energy is increasing from 2.9 to very high. That is the UV band gap energy graph.
Band gap energy was calculated equal LC by lambda formula.
That is
I missed this class.
Before preparation, you have to check all the details, and then you can proceed for upcoming conference.
You said that it is 0.4 times KDP, right? Have you ground the KDP at your laboratory and brought the crystals into the...
No, sir, only in literature values. I didn't do KDP lab, sir.
Okay, that's all. Like that only you are comparing. So generally you have to grow the crystals at your place and bring the same. Then only you can clearly
Come back.
Okay. The particles, so many other parameters are involved in it.
Since you have mentioned that there is a smaller defect, right? So if you are growing in the lab, then that will be fine to compare. They are not grown in some other solvent.
Next time I will try.
So at the FTA here. It is right.
Yes, sir. What in the wave numbers, whatever I in this my material presence in my graph.
Whenever you go for the FTA, the small wave number will come on this right side.
Okay. This.
So higher wave number will come in the fingerprint region. The other remaining part is expansion further. Okay.
Okay, sir. Next time is correct. Sorry for it.
One more thing, you have to fix the FTA range 400 to 4000. Okay, there is no 400, there is no 4000, all are content. Okay, thank you. OP 16, just next participant, OP 18.
concentration activities in environmental samples. So we all know that naturally occurring radioactive nuclides, that's uranium, thorium, and potassium, are crucial for environmental monitoring and radiation safety assessment. So conventionally, the concentration activities of these metals are computed or measured using expensive equipments using gamma spectrography. So which is naturally a time-consuming process and an expensive equipment. So this brings to the motivation of our work. Why can't we use machine learning to predict the concentration activities of these radioactive nuclides in samples? So these are the objectives. To develop machine learning models for radionuclide activity prediction and to capture the relationship between these three metals. So if you take a sample, the concentration of uranium, thorium, and potassium, all the concentration activity values are correlated with each other. So we can apply machine learning to predict the relationship between these values. So instead of measuring all the three values using equipments, if we have predicted values of any two of these, we can predict the value of the other radionuclide metal. So existing works if you take machine learning have been applied for radionuclide classification and radiation dose and accuracy improvement. So, but they do not focus on values predicted. So if you take, you can't say an exact concentration value. So our work focuses on predicting the uncertainty in the concentration predicted. So this is the data set that we are using. We have manually collected. So our data set has around 80 samples, and each sample includes the activity concentration of these three radionuclide metal, and each of these measurements are recorded as x plus or minus sigma. That's the action value plus the associated uncertainty. So in this data we also have MDA values. So though we have a very limited data set, we have performed we have filled those missing values, and we have performed data augmentation. Data augmentation is like we have generated synthetic samples based on our current data set, so as to increase the data set size. So because machine learning requires a huge data, so after data augmentation, we have trained several machine learning models and evaluated them. So instead of using a single machine learning model, we are proposing a hybrid model that's best performing for our case. So the relationship between these three metals is not usually linear. So as we can see, the linear model is not performing that much, and our random forest model performs better across all types of models that we have evaluated our data set on. And so we have proposed a hybrid model, that is to capture the linear relationship between the data. We have used the linear regression plus a random forest for capturing the non-linear relationship. So for predicting the uncertainty value, we have used quantile random forest that gives the range in the prediction. So this is the results that we have obtained. So the mean absolute error for our hybrid model is around 13.33. That is, the mean absolute error is calculated from the actual values and the predicted values. Difference between the actual and the predicted values. So these are the limitations. Like though we have a limited data set, we can extend our work to more diverse data sets, and instead of using only these three values as the features, we can also, if we can get other environmental features as input, our model can perform better. So this is the conclusion. So our hybrid model achieved best accuracy, and it can be applied for predicting radioactive nuclide in metals. it is being collected by our physics department. So yeah, 80 from we have collected
already data available. Only used in the machine learning. Okay.
Yeah.
Okay. Jayashree, I have one doubt because I am zero about machine learning. You have used 3 different models.
Yes, sir.
The output is almost similar. 34, 30, 32. Almost similar.
Yes, sir.
Then how you can justify this? If it is huge difference, we can say concentration will vary or reduce or will increase. If it is almost the same, what is the?
Yes, sir. But if we increase the data set, those small values in the accuracies will be different in. Yeah. With limited data, the difference will be less, but greater the data set size, the accuracies will be varying in a large difference.
Is there any real world application?
Yes, sir. So we don't have to use instruments to compute the concentration activities, sir. So radioactive concentration, it's measured in PQ per kilogram. So if these 3 values, uranium, thorium and potassium, if we can measure any 2 of these, we can predict the third one more accurately instead of using equipments and spending time in that.
Any other questions for the?
Yeah, sir, very interesting. You said 2 radionuclides measurements is thorium or uranium for prediction of potassium.
So if it is 1 is measured and then 2 can be predicted in your machine learning. If you have data sets, because you can have the natural radioactivity, samples data you will have in the lakhs, you can have in the literature. So any correlation on the machine learning over is possible. Very good. So then it's a very.
This is for this we have used single output models. So there are multi output machine learning models which we can use to predict two activities. Give them one. That will further increase the scope of our work.
Even I appreciate even 2 radionuclides because for sodium iodide detector is very comfortable. Many labs have. They can measure 2 because the energy difference, the 3 among 3, If they measure potassium and uranium, you can thorium. There is a lot of difference in energy. So in the sodium detector, it's a very comparatively cheap compared to HPG. So so all 3 has to be measured in the natural because it's what I'm from Atomic Center, I'm environmental. So this actually government of India is Indian documents data, especially this norm they give naturally occurring radioactivity material. Even all the nature, say even our spices, whatever, good banana, everything, potassium, these 3 things will be there. So if the correlation between measurement of any 1 or 2 is measured, then especially in Indianized data, there is no discovery or thing, this measurement data. But of course, whatever data available, many are from almost 60% is from China, other countries only have. Even say coriander, turmeric, there is no specific data for us actually now. What is it's a naturally occurring radionuclide. So this would be very useful if you, sir, I think Chandrasekhar sir, physics department, so you are from computer division, this would be, sir, this we can, because one of the unscared report, our data report is Indian representative data. It is not a big work, but it's a high time consuming experimental data. All the sample, say coal ash, everything we have to find out. That is not a big thing. It's not a discovery big. But Indian, because whenever, say in natural soil, also say fertilizer, bricks.
Inner barcode should be the highest values comparatively with the other one, and show the highest value of 8.26 and 1.14 to 0.2. And then this excessive lifetime cancer was more in children comparatively to the adults. And these are all the conclusions which I withdrawn. And this one, polonium-210 dominates with the lead, and it was more comparatively in the children's compared to the adults. So as you see, Barakuda showed me the highest value of polonium accumulation, 210 polonium. And then this, why, definitely you'll have a doubt why Barakuda has more amount of radionuclides compared to the other fishes. It is because it is a predatory fish compared to the others. We have a process known as biomagnification, in that it gets readily accumulated and consistently concentrated in each tropic level. That is why this Barakuda showed me the highest values. And this one, children were the most radio sensitive compared to the others, adults and everywhere. It's because how much they were more, in the sense 3.7x they were more compared to the adults. And this is the final bioaccumulation pattern. As of I was repeating again and again, Barakuda showed me highest value compared to the ladyfish. Ladyfish was really slower. And my final recommendation is that this has some invasive dietary guidelines to follow, and I found something in the new fishing method, which is invasive method, that is known as bottom trawling. That what they do is they take the heavy nets and then they will just rub along the seabeds, so that they are replenishing this sand, and then the radionuclides are often distributed across the ocean, and then it is getting accumulated inside the fishes. And for the further investigation is needed in this field, and then regular monitoring programs should be done. And these are all my recognized works in our lab from our guide, and these are all the papers but it is in the different sites. It is in Kanyakumari and this is in Chennai, but my work is on the Rameshwaram coastal stretch. And these are all my references. Thank you so much.
My sincere appreciation for your nice presentation. Thank you, sir. Again, I want to ask one out of question. Is there any specific reason?
Yes, sir. In my college, everybody were concentrating on only biological aspects. But this was different from my biology aspect. Radiation was involved in biology, so that it was interesting from other fields. That is why I did this. But this area and all was selected by my guides. I had to know.
That is my actual question. Why specifically in that particular area?
That's what it.
Since I know so many people, they lived more than 100 years only by taking dry fishes. Right? Now everything has changed. Is there any specific reason?
Yes, sir. It has a lifetime, sir. A half-life. It is a daughter particles of uranium, thorium, and potassium. I think our parents might have lived in that half-life period, so that they would have escaped. But now, in the future, polonium and the 210 activities are more, so that in future you'll get some effects on things. Not now, in future, if they consistently eat the dry fish.
Sorry, I interrupted. Okay. So this natural radioactivity. Okay. So this actually this low level, this part and parcel of our evaluation. We should not use. There is no proof below this. I think your dose levels are very low. You put it as a low level activity in that equation, that risk you are estimating. That is also very negligible. That is not proved, and lower level there is no thing. I think this is, you cannot publish. I think you should not use the risk also, because natural no. Even if you fly a higher frequent flyer pilots, they receive more radiation, cosmic radiation. If you go, that is not even banana having a potassium core. No, that's a natural.
Yes,
there is no proof of this. Only thing is, whatever the activity finding is nice actually. That is part and parcel. This is our body will adopt it. Lower level. Say for a small cut in our when we are shaving, automatically small cut it automatically healed.
Yes, sir.
So it's part of our body mechanism. This low level, nothing is in this case not true. Even it will be against our because this natural radioactivity there is no in the world wide risk. We can use it if it is artificial, whatever more than the natural. So this has to be. I think whatever you mentioned, carbide is cancer or one. It is against. They said no only.
Just he generated a baseline data for future work.
What I'm saying is risk. The name, title. Your title is risk,
Yes, sir. Risk.
Consumption of dried fish.
Yes, sir.
There is no risk at all. Natural radioactive. That's a polonium. Natural radioactive. That's what they call. Nothing is. If it is concentrated, if it is whatever uranium, thorium, concentrated, more than consumption of concentrated. If you artificially concentrated, then it will be So whatever the natural items, whatever comes in, no.
There's no effects.
It's a government rule. Not only Indian government, it's IA International Atomic Energies. So only higher level only radiation. So lower level, natural level, no, it's a beneficial basic. It's a beneficial to our even our immune system mechanism, repair mechanism will be activated, more active. So,
Yes, sir. I just compare the 6 species, not with it is below the range of reason.
This array in the sense we have to propagate the message in the natural radiation level, lower level.
Okay.
Lower level it's not at all through no risk at all. Even though it's a controversy, it's beneficial. Even there are radium exposure, people it's a healthy treatment, many are okay. Naturally. Once the level only if it's going the higher level, then it's a different issue. That is obviously it is a fruit. This natural level, because there is no zero level radiation, no. You are also now also you are receiving, I am also receiving, in your body radioactivity is there, so much not only everywhere, there is no place zero level radiation.
Okay, sir. Thank you, sir.
Actually, whatever sir said, my ultimate aim is that's whatever sir said. I simply asked what is the. I hope he can understand.
Yes, sir. I understood, sir.
Right. Okay.
But it's wonderful work. It's good work actually.
Thank you, sir.
Finding radioactivity in a very low level is not easy. You know, if you convert in 1 becquerel in a gram, kilogram, how many? 10 power minus that many kilograms. So it's a highly accurate measurements. It's a highly efficient methodology.
Thank you, sir.
It's a highly technically sound. Whatever we interpret, no, it's there are still, of course, biological, no, it's a public opinion. It would be very useful for us.
Okay, sir. Thank you, sir.
Any other suggestions? Any other possible that to present? Okay.
If there is no questions, we can conclude this session. Thank you. It's very good opportunity for session chair. So to Dr. Chandrasekhar, Dr. Anurag sir, and other amazing committee. Thank you so much.
My sincere appreciation to all the presenters as well as I am really honored to be a part of this program, and my sincere thanks to the organizing committee, Dr. Chandrasekhar sir, Anand Babu sir, and Rajesh sir. Thank you so much.
Thank you, sir. I request Anand Babu sir to honor the present token of appreciation to the session chairs. And what is yours, kindly? Next, I request sir to kindly present the token of appreciation to the session chair, Dr. P. Krishnan. Thank you, sir. And we'll now break for tea. And participants are requested to come back again to the same menu after 10 minutes. So now we can go for tea break.
P. Raja sir and Dr. K. Semiconductor sir. Let's give a round of applause. Now I request Dr. K. Semiconductor sir. Good evening, all. We now gather here for a valedictory function of the 5th International Multifunctional Materials and Radiation Measurements. May I request the dignitaries to kindly occupy the dais. It's now my privilege to invite Dr. Marcella Moses Kennedy, Head of the Department of Physics, SSN College of Engineering, to deliver the welcome address.
Hello. Distinguished Chief Guest, respected valedictory speaker, Dr. J. Raj, esteemed dignitaries, invited speakers, faculty members, research scholars, and dear participants. A very good afternoon to all of you. It is my great privilege and honor to extend a warm welcome to each one of you to the valedictory function of the International Conference on Multifunctional Materials and Radiation Measurements, ICMMRM 2020. Over the past 2 days, this conference has served as a vibrant platform for intellectual exchange, bringing together researchers, academicians, and industry experts from diverse domains. The deliberations, presentations, and discussions have truly reflected the evolving landscape of multifunctional materials and the critical role of radiation measurements in science and technology. We are especially honored to have with us today Dr. Jason Karmaraj from the Environmental Survey Laboratory, Baba Atomic Research Center, Kalpakkam, as our valedictory speaker. His expertise and contributions in environmental monitoring and radiation assessment are highly inspiring, and we eagerly look forward to his insights. I take this opportunity to express our sincere gratitude to all the keynote speakers, session chairs, and presenters for their valuable contributions which have made this conference both meaningful and impactful. I also extend my heartfelt thanks to all participants for your enthusiastic involvement and active engagement throughout the sessions. My special appreciation goes to the organizing committee, faculty members, student volunteers, and staff of the Department of Physics, SSN College of Engineering, whose dedicated efforts ensuring the smooth conduct of this conference. As we come to the close of ICMM 2026, I am confident that the knowledge shared, collaborations initiated, and ideas exchanged here will continue to inspire future research and innovation. Once again, I warmly welcome you all to this valedictory session and wish you a fruitful and enriching experience. Thank you.
Thank you, sir. We now move to the honoring of our esteemed guest, Dr. Jason Dharmaraj, and I request Dr. S. Marcella Moses Kandi, Head of the Department of Physics, to kindly present the memento. Thank you. It's now my honor to introduce our distinguished faculty speaker, Dr. Jason Dharmaraj from Kalpakam. I now request him to kindly deliver the valedictory address.
Respected Head of the Division, Head of the Department, Physics Department, and other faculty members and organizers of this international conference. First of all, I thank the organizers for inviting me the opportunity to give them just 2 minutes only. Of course, I'm from the Bob Atomic Research Center. I'm so happy. I think this SSN College has organized this conference, especially motivating the students, engineering students, the 2 engineering students. So why I am saying it's actually my lab, environmental survey laboratory, is part of the, we are working under the crisis management group. So coming under, because whatever the government policy decisions, even in our security and our radiation protection, because one of our policy is, in Government of India, of course, this climate change. So in 2040, we have to reduce 50% of carbon reduction. So obviously, there is no, we need to have power. Without power, there is no economic development. So countries' development, so solely depend on the core energy sector. So what is the alternative? Obviously, the nuclear energy, which is clean and green energy. So government has taken the initiative, even though the parliament has amended it is amended that is, even private parties can nuclear power plants can be established in a country, because we have the huge energy demand is our power sector we need to have. So there is obviously, we have the manpower, the human energy sector we need to have. Huge demand is coming years, it has to come, especially highly talented, skilled manpower. So this international, obviously I congratulate and appreciate the physics department to introduce the nuclear radiation. I think nuclear radiation is not a public or in the private domain, it is not that much applicability, or it's a fair concept only. Of course, in future, it is recognized that nuclear energy is a clean and green energy. So this conference, what my request is, so we have, because the energy sector, in order to for India's core program, of course this involves our security and as well as our economic development depends purely, this is because I especially climate change, so once my crisis management group top officials, government of India, which is under Prime Minister of India, when he was, if we continue the emission of carbon, our future generation, our future children, human beings, especially in the developing countries, survival is the question. It's impossible if you are not taking steps. So that much government has recognized, not only our government, other developed countries also have taken. So that's why they have drastic steps. It's from now nuclear energy is just 2% or 2.5%, 3%. So in order to curtail the thermal power plants and coming to the nuclear, no, it's highly challenging. So what I want to say is, so our highly skilled Bob Atomic Center recruitment is every year at training school. That's prestigious. It's like every year IAS, UPSC conducting. No, it's a prestigious. It's all disciplines: physics, chemistry, engineering, computer science. Because only one example I will give. This is a Parliament Act. Even IAS, IPS in the say 100 vacancies IAS, 155 IPS. It's a standard. UPSC cannot take one extra post. But in this case, if it is they conduct through gate as well as non-gate in the entrance exam, and the students in the interview, say if it is 100 per mechanical engineers, thousands will be called for the interview. They will be given the second AC fare or third AC. I think even flight also they will give now. In case of remote locations, they will be given accommodation for the interview in Mumbai. What I want to say, that's a high level. In the interview, if they feel the committee has the power, no other committee, even UPSC doesn't have the power. Committee has the power. If the committee feels they want to take 100, but the 200 candidates are outstanding, excellent, they can take the 200. This is the Parliament Act. This is 1968. So the Homi Jagangi Baba, through the Parliament Act, it is. What I want to say is a nuclear pool of engineers, talented, highly talented, for core structure, especially in the power sector in coming year. So this is prestigious colleges or this college. Through this type of conferences, I think people, students have to be motivated. Already this is one of the. So what my request is, it has to percolate to the all engineering students, even for nuclear power plants. Interview committee, mechanical committee, one of the members, last 5 years opportunity I had. So most of the students get topper, even I interview one get mechanical, all India topper also have come. So I motivate, because what I said, your college has to be your student highly skilled person, not only, even of course private also they are the building plans, but in the core, India's development and core framework, more students have to come from your college, and not only from college, your conference, it will percolate to other college. So this initiative I appreciate, I congratulate. Once again, I thank for inviting me for this Valedictory program. Thank you, sir. Thank you.
Thank you, sir, for your insightful talk. And now we are moving to the most awaited prize distribution ceremony. And I request Dr. P. Rajesh, sir, to kindly announce the winning list of the oral and poster presentation.
Good evening, all. We have totally 10 best paper presentation awards. Actually, we decided to proceed with only 3. That is, best oral presentation 3 awards and best poster presentation 3 awards. And the competition was very huge, and upon receiving very huge number of papers, and the judges have given almost equal marks. All the students presented very well, and we decided to increase the award from 3 to 5 in each session, that is in the oral and the poster. And I am very happy to read the winners of oral and poster presentation, 5 oral presentation winners and 5 poster presentation winners. All are equal. There is no 1, 2, 3, 4, 5. Okay. Yeah, I am starting with oral presentation. Sri Shi Amrita Vishwa Vidyalaya, Coimbatore. I request Dr. Jason to our head of the department to. Distribute the certificates. Alofi Mary, College of Engineering, Gindi, Anna University. Mohanraj Yam, Wales Institute of Science and Technology and Advanced Studies, Chennai. Praveen Joshua, SSN College of Engineering, Chennai. Hema Malini, St. Joseph's College, Autonomous, Trichy. Best Poster Awards. Yam Avudai Koti, Kalasalingam Academy of Research and Education. Santosh Raj D, B.S. Abdul Rahman, Crescent Institute of Science and Technology, Chennai. Sirumalar A, Sri Siva Subramania Nadar College of Engineering, Chennai. Exciton T, Sri Siva Subramania Nadar College of Engineering, Chennai. Santosh S, SA Engineering College, Chennai. And we would like to give one more award to the Best Contributed Award names. I think we have received 25 plus abstract from Savita Engineering College. So maybe one of the students from Savita Engineering College. It is the Best Contribution Award. Congratulations to the winners. Thank you.
Thank you, sir. And I now request Dr. G. Anand Babu, Department of Physics, to propose the vote of thanks.
Good evening, everyone. Good evening, everyone. It is my privilege to propose vote of thanks on this memorable occasion. On behalf of the organizing committee, I extend our heartfelt gratitude to our distinguished chief guest, T. Scientific Officer, Environmental Monitoring and Assessment Division, Baba Atomic Research Center. Eminent speaker, respected delegates from across the country, your presence, insights, valuable contribution have truly enriched this international conference and make it a grand success. I would like to sincerely thank our keynote speaker, invited speaker, session chairs for sharing their knowledge, expertise, and thought-provoking ideas. Your session have inspired meaningful discussion and opened new avenue for collaboration. We are deeply grateful to all the participants for our active involvement, engaging questions, enthusiasm throughout the conference. I would also like to thank SSN management and the principal for their generous support and trust, without which this event would not have been possible. A special word of appreciation goes to organizing committee, volunteers, research scholars, non-teaching staff, and the technical teams for their tireless effort, dedication, seamless coordination in making this event run smoothly. With this, we come to close this wonderful gathering. We hope the connections made and knowledge shared here will continue to grow beyond this platform. Thank you all once again. We wish you a happy journey and look forward to meeting you again in the future.
Thank you, sir. As we come to the close of ICMMR 2026, I request everyone to kindly rise for the national anthem.
पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you all for your presence and active participation, and we wish you a safe journey and pleasant journey. All requested to collect the certificates from the registration desk. I repeat, all are requested to collect your certificates from the registration desk.